Lucene Architecture. Here you can see the system architecture diagram. Apache Lucene is a free and open source search engine software library originally written in Java by Doug Cutting. It is supported by the Apache Software Foundation and is released under the Apache software license. Lucene is widely used as a standard foundation for non-research search applications. Illustrated in this figure, the whole architecture of Lucene system is made up of external interface, index core, and basic structure encapsulation of the three major components, of which the index core part is apparently the most important. The Lucene API is divided into several packages. org.apache.lucene.search provides the data structures to represent queries, that is term query for individual words, phrase query for phrases, and boolean query for boolean combinations of queries, and an index searcher which turns queries into top docs. A number of query parsers are provided for producing query structures from string or XML. org.apache.lucene.analysis define an abstract analyzer API for converting text from a reader into a token stream and enumeration of token attributes. A token streams can be composed by applying token filters to the output of a tokenizer. Tokenizers and token filters are strung together and applied within an analyzer. Analysis common provides a number of analyzer implementations, including stop analyzer and grammar-based standard analyzer. org.apache.lucene.index provides two primary classes: index writer, which creates and adds documents to indices, and index reader, which accesses the data in the index. org.apache.lucene.store define an abstract class for storing persistent data, the directory, which is a collection of named files written by the index output and read by an index input. Multiple implementations are provided, but the fs directory is generally recommended as it tries to use operating system disk buffer caches efficiently. org.apache.lucene.document provides a simple document class. A document is simply a set of named fields whose values may be strings or instances of reader. org.apache.lucene.util contains a few handy data structures and util classes, that is fix, bitset, and priority queue. org.apache.lucene.codex provides an abstraction over the encoding and decoding of innoted index structure, as well as different implementations that can be chosen depending upon application needs. Here the query request is connected to Lucene search. Lucene search, the searcher, and Lucene analysis, language analyzer, are inside the external interface. Lucene search, the searcher interacts with Lucene queryParser. Lucene search, the searcher is connected to search result. Lucene queryParser, the queryParser interacts with Lucene search and Lucene analysis, language analyzer. Files to be indexed are connected to Lucene analysis. Lucene analysis and Lucene search are connected to Lucene index. Lucene index, the indexer, and Lucene storer are in index core. Lucene index interacts with Lucene store. Lucene store interacts with index files. Lucene documents and Lucene util tools are in basic structure encapsulation. Here you can see another architecture diagram of Lucene. Here these gray lines are protocol, and these white lines are implementation. And here you can see a user interface. Below that you can see search, and below user interface and search you can see below and next to search you can see index, this here access and maintenance. Next to index you can see the storage. Below search and index you can analysis is there, and below analysis corpus is there. Here you can see the architecture of Lucene. The Lucene is not a complete full text indexing system, but a full text indexing engine toolkit, which is written by Java language. It offers multi API function and flexible data storage structure, and conveniently embeds in various applications to realize application-oriented full-text index and retrieval. Lucene system architecture has strong object-oriented feature. At first, the index file format, which is unrelated to platform, is defined. Next, the core part of the system is designed as abstract type, and specific platform realization is designed as abstract realization. In addition, some related files related to specific platforms, such as file storage, is also encapsulated as the class. After object-oriented process is performed layer by layer, the index engine system is easy secondary development with low coupling and high efficiency is finally obtained. The class which is related to search in Lucene all contains in org.apache.lucene.search and index writer is the most important class. Index writer offers 3 common constructor functions and 1 private constructor function to instantiate one object, and parameter in constructor function is the index directory. This parameter can be taken as a directory object, file type object, and index reader type object. Lucene system architecture and source code organization graph are shown in this figure here. Here you can see the index lines. Here the file in the regarding index files to be indexed are connected to org.apache.lucene.analysis, and it is connected to org.apache.lucene.index, and it is connected to org.apache.lucene.store, and org.apache.lucene.store is connected to index. With regarding you can see the searching lines here and here. Here the query is connected to org.apache.lucene.analysis, and org.apache.lucene.analysis is connected to org.apache.lucene queryParser. queryParser is connected to org.apache.lucene.search, and the org.apache.lucene store is index is connected to org.apache.lucene.store, and it is connected to org.apache.lucene.search, and it is connected to org.apache.lucene.search.similarity, and it is connected to query result. Here you can see Lucene application structure. Lucene enables to add the indexing and searching capabilities to applications and hides the complicated implementation of indexing and searching behind a simple to use API. In this way, the Lucene acted as an independent layer. An application sit on top of it, which is depicted in this figure here. By layer upon layer, object-oriented processing, Lucene achieved to be a high performance, loose coupling, easy to secondary exploitation search engine system. Here the file system, web pages, database, manual input and gather data, and user get users request and present search results are in application, and index files and search are in Lucene. Here the file system, web pages and database and manual input are connected to gather data. Gather data is connected to index here. Index is connected to index files, and here the user is connected to get user request via query, and get user's request is connected to search. Search interacts with index files, and search is connected to present search result, and present search result are connected to user via results. Here you can see a Lucene indexing mechanism. To index data with Lucene, first of all we must convert it into a stream of plain text, plain text tokens, the format that Lucene can digest. Therefore, other patterns of files must be converted into text before being indexed. Secondly, create a document object with its relevant field objects. Then call the method add document to store the data for indexing. Next, use the specified analyzer to tokenize every word of indices so that data stream can be more suitable to be indexed. But last but not least, write the result back into index files. The process of building full text indices is presented in this figure. Here the .html, .text, .doc and .pdf are in files to be indexed, and .html, .text, .doc and .pdf are connected to document processing. Document processing is in file patterns to converted and add document. Document processing is connected to language analyzer. Language analyzer is connected to indexed files. Here you can see the Lucene architectural layers. Here you can see the search below the index, and below that under index below the index store document analysis. Here you can see Lucene high level diagram in Lucene.NET. Apache Lucene.NET is a C# port of Java-based Apache Lucene. Lucene and hence Lucene.NET stores data in immutable segments. Segments are made of multiple files. Segments automatically get merged together to form new bigger segments, and then all segments are typically deleted by the merge process. This approach is based on what is called a log structured merge LSM design. LSM has become the de facto standard for NoSQL databases, and it is used not only by Lucene but also by Google Bigtable, Apache HBase, Apache Cassandra, and many others. The details of each implementation vary, as does the number of and types of files used. The documents and fields. The Lucene stores documents, and the documents are composed of fields. The fields can be a variety of types like test, string, or int32. Documents may have as many fields as you like. There is no concept of schema, and document don't need to all have same fields. When searching, you can search any field and it will only return documents which have that field and where the data in that field matches the specified search criteria. Writing and reading documents. Documents are written via an index writer and read via an index reader. Although in practice we often use index searcher, which wraps an index reader for searching and reading documents. Lucene directories. We already mentioned that the data is stored in segments. Those segments can be stored via different classes that inherit from Lucene.NET store.directory. Some of these classes, like fs directory, store your local file system and other can store elsewhere. For example, RAM directory can be useful for unit test as it stores the segments in RAM. So one of the things that we must provide an index writer is an instance of Lucene.NET.store.directory. That is the type of directory we want to work with. This diagram here provides the bird's eye view of how the various parts of the system work together. It makes easier to conceptualize the parts of Lucene that we have been talking about here. In the diagram here, the files is in quotes because if you are using RAM directory, say for testing, then there will be no physical file, but rather their representation will be in memory only. Here fields are inside the document. A document is connected to index writer. Here query is connected to index searcher, and index searcher is connected to top docs. Index searcher interacts with index reader, and index reader interacts with index writer. Index writer interacts with Lucene directory. Lucene directory is connected to index reader, and Lucene directory interacts with one or more segments, each comprised of multiple files. Here you can see high-level architecture of Lucene Core here in Lucene 4.0. The Lucene's architecture and implementation has evolved and improved significantly over its lifetime, with much of the work focused around usability and performance, with the work often falling into the areas of memory efficiencies and the removal of synchronizations. Here we'll detail some of the commonly used foundation classes of Lucene, and then look at indexing and searching are built on top of this. To get started, this figure illustrates the high-level architecture of Lucene Core. With regarding text analysis, chain produces stream of tokens from the input data in the field. Tokens are in the analysis chain are represented as a collection of attributes. In addition to the expected main term, attributes that contains the tokens are the token attribute that contain the token value. There can be many other attributes associated with the token, such as token position, starting and ending of offsets, token type, arbitrary payload data, a byte array to be stored, in the index at current position, integer flags, and other custom application defined attributes. For example, part of speech tags. Analysis chains consist of character filters useful for stripping diacritics, for instance, tokenizers, which are the sources of token stream, and series of token filters that modify the original token stream. Custom token attributes can be used for passing bits of per token information between elements in the chain. Lucene includes a total of 5 character filtering implementation, 18 tokenization strategies, and 97 token filtering implementation, and over 32 different languages. This token stream performing specific functions such as tokenization by patterns, rules, and dictionaries. For example, whitespace, regex, Chinese, Japanese, Korean, ICU. Specialized token filters for efficient indexing and indexing of numeric values and dates to support trie-based numerical range searching, language specific streaming and stop word removal, creation of character or word level engrams, tagging, UIM, etc. Using these existing building blocks or custom ones, it's possible to express very complex text analysis pipelines. With regarding finite state automata, the Lucene 4.0 here they requires significantly less main memory than previous releases. In the in-memory portion of the inverted index is implemented with the new finite state transducer. FST package. Lucene's FST package supports linear time construction of the minimal automation, FST compression, reverse lookups, and weighted automata. Additionally, API supports pluggable output algebras, synonym processing, Japanese text analysis, spell correction, auto suggest, and are now all based on the Lucene's automata package with additional improvements. planned for future releases. This is regarding Lucene 4.0. Indexing. Lucene uses well-known inverted index representation with additional functionality for keeping adjacent non-inverted data on a per document basis. Both in-flight and persistent data uses variety of encoding schemas that affect the size of the index data and the cost of the data compression. Lucene uses pluggable mechanism for data coding and for actual storage of index data directory API. Incremental updates are supported and stored in index extents referred as segments that are periodically merged into later segments to minimize the total number of index parts. Document model. Documents are modeled in Lucene as a flat ordered list of fields with content. Fields have name and content data, float weight used later for scoring, and other attributes depending on their type, and with together determines how the content is processed and represented in the index. There can be multiple fields with the same name in a document, in which case they will be processed sequentially. Documents are not required to have a unique identifier, though they often carry a field with this role for application level unique key lookup. In the process of indexing, documents are assigned internal integer identifiers. Field types. There are two broad categories of fields in Lucene documents. Those that carry content to be inverted, index fields, and those with content to be stored as stored fields. Fields may belongs to either both categories. For example, with content both to be stored and inverted, both index and stored fields can be submitted for storing and or indexing, but only stored field can be retrieved. The inverted data can be accessed and reversed using a specialized API. Index fields can be provided in plain text, in which case it will be first passed through index analysis pipeline. Or in its final form of sequence of token with attributes, so-called token string. Token streams are then inverted and added to the in-memory segments, which are periodically flushed and merged. Depending on the field options, various token attributes such as position, starting or ending offsets, and preposition payloads are also stored with the inverted data. It is possible, for example, to omit positional information while still storing the in-document term frequencies on a per field basis. A variant of index field is a field where the criterion and storage of term frequency vectors are requested. In this case, the token stream is used also for building a small inverted index consisting of data from the current field only, and this inverted data is then stored on a per document and per field basis. Term frequency vectors are periodically useful when performing document highlighting, relevance feedback, or when generating search result snippets, region of text that best matches the frequency terms. Stored fields are typically used for storing auxiliary per document data that is not searchable but would be cumbersome to obtain otherwise. For example, it would require retrieval from separate system. This data is stored as byte arrays but can be manipulated through a more convenient API that persists it as UTF-8 strings, numbers, arrays, etc. Or optionally it can be stored using strongly typed API, so-called doc values, that can use more optimized storage format. This kind of strongly typed storage is used, for example, to store per document and per field weights. So-called norms, as they typically correspond to field length normalization factor that affect scoring. Index chain, the resulting token stream is finally processed by the indexing chain, and the supported attributes, term values, position, offset, and payload data added to the representing position list for each term. The term values don't have to be UTF-8 string as in previous versions before Lucene 4.0. Fully support the Lucene 4.0 fully supports arbitrary byte array values as terms and can use custom comparators to define the sorting order of such terms. Also, at this stage, documents are assigned their internal document identifiers, which are small sequential integers for efficient delta compression. These identifiers are epimental. They are used for identifying document data within a particular segment, so that naturally change after two or more segments merged during index compaction. Incremental incremental index updates. Indexes are updated incrementally online, simultaneously with searching by adding new document and or deleting existing ones. Subdocument updates are work in progress. Index extents are common way to implement incremental index updates that don't require modifying the existing parts of the index. When new documents are submitted for indexing, their fields undergo the process described in the before. The resulting inverted and uninverted data is accumulated in new in-memory index extent called segments. Using compact in-memory representation, a variant of codec, periodically these in-memory segments are flushed to the persistent storage using codec and directory abstraction. Whenever they reach a configurable threshold, for example, total number of documents or the size in bytes of the segments, the index writer class. The index writer is a high-level class responsible for processing index updates, addition and deletion, recording them in new segments, and creating new commit points, and occasionally triggering index comparison, segment merging. It uses a pool of document writers that create a new in-memory segments. As new documents are being added and in-memory segments are being flushed to the storage, Periodically, an index compaction merging and is executed in the background that reduces the total number of segments that compare the whole index. Document deletions are expressed as queries that select using Boolean match the documents to be deleted. Deletions are also accumulated applied to the in-memory segments before flushing and while they are still mutable and also recorded in a commit point so that they can be resolved when reading the already flushed immutable segments. Each flush operation for index compaction creates a new commit point recorded in a global index structure using two-phase commit. The commit point is a list of segments and deletions comprising the whole index at the point in time when the commit operation was successfully completed. Segments data that is being flushed from in-memory segment is encoded using the configured codec implementation. In Lucene 3.x, and earlier some segment data was mutable. For example, the parts containing deletions or field normalization weights, which negatively affected the concurrency of writes and reads. To apply the modification, the index had to be locked and it was not possible to open the index for reading until the update operation completed and lock was released. In Lucene 4.0, the segments are fully immutable. Write ones and any changes are expected either as a new segment or a new list of deletions, both of which the new commit points and the updated view of the latest version of the index become visible when commit point is recorded using two-phase commit. This enables to lock-free reading operations concurrently with updates and point in time travel by opening the index of reading using some existing past commit point. The index reader class the index reader provides high-level methods to retrieve stored fields. Term vectors and traverse the inverted index data. Behind the scenes, it uses the codec API to retrieve and decode index data. The index reader represents a view of an index at the specific point of time. Typically, a user obtains an index reader from either a commit point where all data has been written to disk or directly from index writer. Near real-time snapshot that includes both the flushed and in-memory segments. As mentioned in the previously, segments are mutable, so deletions don't actually remove data from existing segment. Instead of delete operations are resolved when existing segments are open. So the deletions are represented as a bit set of live, not deleted documents. Global index statistics are not recalculated, so they are slightly wrong. They include the term statistics of postings that belongs to the deleted documents. For performance reasons, the data of deleted documents is actually removed only during segment merging. And then also global statistics are recalculated. Index reader API follows the composite pattern. An index reader representing a specific commit point is actually a list of sub-readers for each segment. Composed index readers of different points in time share underline subreaders with each other when possible. This allows for efficient representation of multiple point in time views. An extreme example of this is the Twitter search engine, where each search operation obtains a new index reader. Codec API, the Lucene 3.x used a few predefined data coding algorithms, a combination of delta and variable length byte coding. In Lucene 4.0, all parts of the Lucene code that dealt with the coding and compression of data have been separated and grouped into a codec API. This major redesign of Lucene architecture has opened up the library for many improvements, customizations, and for experimentation with recent advances in inverted index compression algorithms. The codec API allows more complete customization of how index data is encoded and written out of the underlying storage, the inverted and non-inverted parts, how it's decoded for reading, and how segments are merged. The 4D view of inverted index, the codex API represents the inverted index that data as a logical 4-dimensional table that can be traversed using enumerators. The dimensions are field, term, document, and position. That is an imaginary cursor that can be advanced along rows and columns of this table in each dimensions. And it supports both next item and seek to item operations, as well as retrieving row and cell data at the current position. For example, given a cursor at field F1 and term T1, the cursor can be advanced along this posting list to the data for the document D1, where the in-document frequency for this term TF can be retrieved, and then positional data can be iterated to retrieve consecutive position offsets and payload data at each position within this document. This level of abstraction is sufficient to not only support many types of query evaluation strategies, but to also clearly separate how the underlying data structures should be organized and encoded, and to encapsulate this concern in codec implementation. Lucene 4.0 codecs, the default codec implementation, aptly named Lucene 440, uses Lucene 4.0 uses a combination of well-known compression algorithm strategies selected to provide a good trade-off between index size and related cost of I/O sets and coding costs. Byte-aligned coding is performed for its decompression speed. For example, posting list data uses variable byte coding of delta values with multi-level skip list, using natural ordering of document identifiers and interleaving of document IDs and position data. For frequency occurring very short list, according to the SIP's law, the codec switches to using pulsing strategy that inline posting with term dictionary. The term dictionary is encoded using a block tree schema that uses shared prefix, deltas per block of terms, fixed line or variable size, and skip list. The non-inverted data is coded using various strategies. For example, pre-document strongly typed values for encoding using fixed length bit align compression similar to frame of reference coding, while the regular stored field data uses no compression at all. Applications may of course compress individual values before storing. Lucene 4.0 codex offers in practice good balance between high performance indexing and fast execution of queries, since the codec API offers a clear separation between frequency functionality of inverted index and the details of its data formats. It's very easy in Lucene 4.0 to customize these formats if the default codex is not sufficient. The Lucene community is already working on several modern codecs including P4 Delta, Simple 9, 16, 64, both likely to be included in the 64, and VS encoding, and experimenting with other representation for term dictionary, for example using finite state transducers. This is about 4.0. The codec API opens up many possibilities for runtime manipulation of posting during writing or reading, for example online pruning and sharding, adding bloom filters or fail fast lookups, for example, lookups, etc., and to accommodate specific limitation of the underlying storage, for example appending codecs that can work with append only file systems such as Hadoop DFS. Directory API. Finally, the physical I/O access is abstracted using directory API that offers a very simple simple file system like view of persistent storage. The Lucene directory is basically a flat list of files. Files are write ones, and abstractions are provided for sequential and random access for writing and reading files. This abstraction is general enough and limited enough that implementation exists both using java.io.file NIO buffers in memory distributed file systems that, for example, Amazon S3 or Hadoop HDFS, NoSQL key value stores, and even traditional SQL databases. Now searching. Lucene's primary searching concerns can be broken down into few key areas which will be discussed now. Lucene's under topics Lucene's query model, query evaluations, scoring, and command search extension. We will begin by looking at how Lucene models queries. Query model and types. Lucene does not enforce a particular query language. Instead, it uses query objects to perform searches. Several queries are provided as building blocks to express complex queries. And developers can construct their own programmatically or via a query parser. Query types provided in Lucene 4.0 include term queries that evaluate a single term in a specific field, Boolean queries supporting and or not, where clauses can be any other query, proximity queries, strict phase, sloppy phase phrase that allows for up to n inverting terms, position-based queries called spans in Lucene parlance that allows to express more complex rules for proximity and relative positions of terms, wildcard, fuzzy, and regular expression queries that uses automata for evaluating matching terms, disjunction max query that assigns scores based on the best match for a document across several fields, payload query that possesses per position payload data, etc. Lucene also supports the incorporation of fields values into scoring, named function queries. These queries can be used to add useful scoring factors like time and distance into scoring model. The large collection of predefined queries allows developers to express complex criteria for matching and scoring documents in a well-structured tree of query clauses. Typically, a search is passed by a query parser into a query tree, but this is not mandatory. Queries can be generated and combined programmatically. Lucene ships with the number of different query parsers out of the box. Some are based on Java CC grammars, while others are in XML base. Query evaluation. When the query is executed, each inverted index segment is processed sequentially for efficiency. It is not necessary to operate on a segment on a merged view of the posting lists. For each index segment, the query generates a scorer. Essentially an enumerator over the matching documents with an additional score index. Additional score method. Scorers typically score documents with the document at a time DAAT strategy, although the commonly used Boolean scorer sometimes uses TAAT, term at a time like strategy. When the number of terms is low, scorers that are leaf nodes in the query tree typically compute the score by passing raw index statistics such as term frequency to the similarity, which is significant, which is a configurable policy for term ranking. Scorers higher up in the tree usually operate on sub-scorers. For example, disjunction scorer might compute the sum of its children's scorers. Finally, the collector is responsible for actually consuming these scorers and doing something with the results. For example, populating a priority queue of the top 10 documents. Developers can also implement custom collectors for advanced use cases such as early termination of queries, faceting, and grouping of similarity results. Grouping of similar results. Similarity class implement a policy for scoring terms and query clauses. Taking into account term and global index statistics as well as specifics of a query, that is for example, distance between terms of a phrase, number of matching terms in a multi-term query, Levestein edit distance of fuzzy terms, etc. Lucene for now maintains several per segment statistics, for example, total term frequency, unique term count, total document frequency of all terms, etc. to support additional scoring models. As part of the indexing chain, this class is responsible for calculating field normalization factories factors, weights that usually depends on the field length and arbitrary user specified field boosts. However, the main role of this class is to specify the details of query scoring during query evaluation. As mentioned before, the Lucene 4 provides several similarity implementation that of well-known scoring models. TF, IDF with several different normalizations, BM25 information based, divergence from randomness, and language modeling. Common search extensions. Keyword search is only a part of query extension. Keyword search is only a part of query execution for many modern search systems. Lucene provides extended query processing capabilities to support easier navigation of search results. The face setting module allows for browsing drill down capabilities, which is commonly in many e-commerce applications. Result grouping supports folding related documents, such as those appearing on the same website into a single combined result. Additional search modules provide support for nested documents, query expansion, and geopartial search. Here the add or update is connected to the document. Fields are in documents, and document is connected to the document writer documents writer via per field stored values, and documents is connected to text analysis chains, and document is connected to chains, and it is connected to a document writer via per field token streams. And via text analysis chains. Delete is connected to a document writer. Document writer indexing chain and segments are inside index writer. Document writers are connected to indexing chains. Indexing chains are connected to segments. Segment is connected to segments in codec via flush or commit. Here the segments can merge here, and the segments are inside codecs, and segments are connected to segment reader via open or reopen, and segment reader is connected to collection stats and term enum and doc and position enum. Collection stats and term enum and doc and position enums are connected to scoring API here. Segment reader and collection stats and terms enum and doc and position enums are in index reader. Index reader provides retrieve stored values here, and here the query search is connected to search is passed to a queryParser. queryParser is connected to text analysis chains, and queryParser is connected to query, maybe via sometimes via text analysis chains. Via text analysis chains. Query is connected to scoring API, and scoring API is connected to collector. Collector provides ranked results. Here the codex is connected to directory. There are files in the directory, and directory is connected to storage. Here you can see Lucene Architecture in a different view. Here the analyzer, index writer and document handler in indexing. Here the document handler is connected to index writer. Index writer interacts with the analyzer. Here the an index writer is connected to directory. Directory is in storage, and directory interacts with index searcher. Analyzer, query parser, index searcher, response visualizer, and search request are inside are in searching. Here the search request is connected to query parser, and query parser interacts with analyzer. Query parser is connected to search index searcher. Index searcher interacts with directory, and index searcher is connected to response visualizer. Here you can see package structure of Lucene version 1.4.3. This figure shows one of the earliest version of Lucene still archived, version 1.4.3. Recall that a simple test of structure suggests the selection of a package at random and ask if this package changes, which other packages it will most likely impact. Take index for example. Clearly both the query parser and spans depend on it, and hence might be impacted by any change to index, and that curved line shows that search depend on it too. In this easy of dependency identification characterizes the entire figure, making this a well structured design. Bravo Lucene, you are off to a good start here. Here you can see dependencies between among D, query parser, spans, RU, standard, index, search, util, analysis, document, and store. Here you can see a package structure of Lucene version 2.0. This figure shows version 2.0. Note that we shall not investigate every release, but eventually space milestone among the entire release path, and the simplicity of the interconnectedness continues despite the number of methods rising from version 1.4.23's 1637 to version 2.0's 2085. The number of packages has fallen from 11 to 10. This has prompted a slight fall in potent coupling efficiency from 41% to 37%, but nonetheless good design principles clearly master this system. Here you can see the dependencies among standard, query parser, spans, Lucene, index, search, document, analysis, util, and store. Here you can see the package structure of Lucene for 2.4. Presented here in this figure. Version 2.4, although far from an obviously bad structure, shows this first signs of distress. True, many of the packages stand all clear in relationships to their neighbors, but now some do not. In particular, search and index seems to have become embroiled in one another's affairs. This mild degradation of structure, however, belies the tumultuous changes that have taken place behind the scenes. Where the version 2.0 had 2085 methods, version 2.4 has more than double in size to 4176 methods, and where version 2.0 had just 9,767 transitive dependencies. Version 2.4 sags beneath a burdensome 48,370 transitive dependencies. Some structural crack has opened deep down on method level to trigger this five-fold increase in dependencies, a crack which Lucene's programmers have never detected or seal, and which plagues later revisions as well, as we shall see. Not only the number of dependencies dramatically increased, but the depth of the program, average length of its transitive dependencies has increased to, jumping from version 2.07 to version 2.8's 8.7, not only laying more tracks over which ripple effects may trundle, but extending those tracks to shunt spurious impact further afield. Still, this structure presents no unresolvable problems. Focused design could reinstate simplicity enjoyed by the earlier versions. Here you can see the dependencies among Lucene, payload, queryParser, function, standard, index, search, analysis, document, spans, util, store, and cache. Here you can see the package structure of Lucene 3.0. Alas, the version 3.0 shown here in this figure seems to continue ever so slightly the downward trend. Again, the figure does not present an irredeemable structure. We can tease apart the package to see how most connect with one another. The task, however, has become harder. Both analysis and spans have been sucked into a tangle sparked by search and index. Predicting the impact of changing any of these four packages would now seem to require an automatic investigation on all others. Contributing to this increase in interconnection is the addition of 800 methods to this revision. And even though the number of transitive dependencies has admirably fallen to 46,970, nevertheless average length has again risen, this time to 9.3. Is a system structure beyond hope? Not at all. Many of the packages enjoy clear dependency relationships with other colleagues. Just around the corner, however, lies version 3.5 and a surge of transitive dependencies, which, though not immediately fatal, proves a distress resistant to all medicines. Here you can see the dependencies among messages, standard, queryParser, payload, function, Lucene, index, search, spans, analysis, token attributes, document, util, store, and cache. Here you can see the package structure of Lucene 3.5. On positive note, the version 3.5 shown in this figure introduces an extra 3 packages, bringing to the total 18, in an attempt to distribute the separate the system's functionality. The generous might also offer that the package structure has clearly decayed again from previous versions. That decay remains somewhat localized. Bad boys analysis spans, search, and index continue to terrorize the rest of Lucene's town's largely well-behaved population. But the generosity ends here. For despite adding only after 100 and 800 methods, the number of revisions 3.5's transitive dependencies has soared to 109,357, and average length of those dependencies hits 11 methods long, a sad maximum for the entire evolution. Given this phenomenal rise in the structural complexity, we wonder how the package design seems as good as it does, and indeed any such harmony Harmony proves short-lived as the strain finally destroys all semblance of control in the next revision milestone. Here you can see the dependencies among messages and function payloads, standard collation, FST, Lucene, STD31, index, search, spans, analysis, token attributes, packed, document, util, and store. Here you can see the package structure of Lucene 4.0. The revision 4.0 shown in this figure adds 1600 methods to the previous revision, bringing the total to 8,474 and rising the number of transitive dependency relatively modestly to 16,211. But as can be seen from this figure, something terrible has happened. The burgeoning interconnectedness of previous revisions has suddenly systemized, causing the structure to implode into the dreaded ball of tangled dependencies that makes code impact prediction widely unreliable. Through this revision adds another 2 packages, rising the potential coupling efficiently to 43% and reduces slightly transitive dependency length to 10.4. But the sheer effort of controlling this vast number of transitive dependencies has simply broken the system. It will not recover. Here you can see the dependencies among Lucene, payload, mutable, index spam, similarity search, util, Lucene, and packed, codec, automatic, document analysis, store, token attribute, FST, Lucene for 0 values, and per field. Here you can see the package structure of Lucene 4.5. In revision 4.5 shown in this figure, some heroic action has reduced the number of transitive dependencies to 106,242 while raising the number of methods to 9,562, and perhaps some packages have managed to distance themselves from the ravenous black hole spinning manically at the system's core, but the work is too little or too late. Here you can see the dependencies among mutable, Lucene 4.3, Lucene 4.2, payloads, span, Lucene, and Lucene 4.1, Lucene 4.0, compressing, index, per field, search, codecs, similarities, util, package, store, Lucene 3x, automation, analysis, FST, store, document, and token. Here you can see the package structure of Lucene 4.0. Revision 4.0 shown in this figure attempt to tame the beast by removing 200 methods, yet this curiously result again rising the number of transitive dependencies to 13,556. Does the revision 5.0 look as bad as revision 4.5? Well, perhaps not. Something will look a little cleaner. We would not, however, allow this to blind us to the grand DCD structure on this figure. The system weeps in pain, predicting the cost of changing any of those central packages has become foolhardy. Here you can see the dependencies among mutable, Lucene 5.0, payload, Lucene, and block 3, compression, index, per field, spans, codecs, packed, similarity search, store util, document analysis automation, FST token attributes. Here you can see comparing Lucene's transitive dependencies per method ratio. To understand what happened to destroy the system's initial structural integrity, we must examine the version 3.5. Again, this may not look like the worst structure, but this revision here herald the changes that lead to eventual ruin. The main change was not just one of size. Bigger systems need not necessarily fall to poor structure. Revision 3.5 increased the number of methods by 35%, but revision 2.4 increased the number of methods by more than 100% without wrecking the overall organization. Instead, the primary culprit were the number of transitive dependencies and their distributions across the system. The sheer number of new transitive dependencies introduced in revision 3.5 is astounding, rising from 46,917 to 109,357. This brought the dependency to method ratio to an artery hardening 16. Here you can see Lucene releases, and here the transitive dependencies per method. Here you can see fitness here, and here the JUnit, and here the spring core here, and here the sparkling, and here the Lucene. Here you can see percentage of Lucene transitive dependencies spanning fewer than 3 packages. The dependency to method ratio has already been too high in previous revision. However, the transitive dependencies largely confined themselves to just 1 or 2 packages. The revision 3.0, 95% of all transitive method dependencies are either terminated in their originating packages, so in the package just one dependency away. This gave a hope that the changes might in some sense limit themselves to a region close to the origin point, leaving few changes to spill out all over system and to defy cost prediction. Revision 3.5, however, saw that the figure plummeted to just 75%. This means that 25% of all revision 3.5's transitive dependencies spilled into 3 or more packages. Combining both of these factors revealed that more than 33,000 dependencies lie in wait to catapult changes far from their origin. More than anything else, this dooms the product to further structural decay. This concludes the examination of Lucene package level structure. So here you can see Lucene releases, and here percentage transitive dependency is less than 3 packages. Here you can see Lucene. Here you can see Lucene's transitive dependency CDF. Let us attempt to append an objective scoring of Lucene's structure. Its final revision examined here 5.0. We shall use the average of 4 factors. This first measures the Lucene attempt to limit number of dependencies that are possible to form. Second and third attempt to capture transitive dependency length, and fourth attempt to capture the number of transitive dependencies. Of course, large systems will always have more dependencies than small systems. We cannot say a system A is more well structured than system B simply because it has fewer dependencies. Instead, we must derive measurement that can be fairly compared by either normalizing for size or making the measurement in some sense self-referential. First, we shall measure its absolute ideal efficiency. This analyzes the structure's potential coupling and basically asks how many methods are encapsulated away from other methods, and thus how many dependencies could conceived by be created. If every method were put in one class, then every method would be visible to every other, and so the efficiency would be 0%. The value rises, more methods are made private and put in separate packages, package private classes, thus increasingly encapsulation method from one another. The Lucene scores 44%, indicating that has at least attempted to encapsulate this functionality, but much more could be done. Second, we shall measure the length of the Lucene's transitive dependencies in the form which allows fair comparisons between programs. For this, we shall use CDF graph showing how long Lucene's transitive method dependencies are as a percentage of its longest transitive dependency. This figure here, we see that half of the Lucene's transitive dependencies are shorter than 45% of the length of the longest transitive dependency. This is bad. System's resistance to ripple effect relies on most of its dependencies being short. Half of the JUnit's transitive dependencies, for example, are not only 30% of that length of its longest dependency. As you recall a figure that rises with improved structure, we shall use 100 minus this figure. So the Lucene will score 100 minus 44, 55 value, which could be closer to 70. The third factor we shall use the already has been discussed, the percentage of method that span two packages. So a figure around 75%, 75.5%. This sound high, but with modern structuring technique there is a little reason for this value to be less than 90. Finally, we need the factor that measure how many dependencies wiggle through a system. As a fewer number of dependencies, the better. To normalize for size, we would like to measure the number of dependencies per method. Here we must unfortunately estimate an industry lowest possible score. Some research suggests that 25 seems an appropriate figure. If the system contains more than 25 dependencies per method, then the system structure is so bad that all other metrics lose their importance. We saw earlier that Lucene has huge 12 dependencies per method. So the figure we shall use is 25 minus 12, 13, expressed as percentage of 25, giving 52. As a figure, this figure presented, the other systems reach as low as 6 dependencies per method, a figure which yields 70% for this matrix. This gives the Lucene the final score of 226.5 divided by 400 points, or 57%, with firm structural principles. Modern program easily score 80% above, score above 80%. So this is poor score, indicating alas a poor structure. Lucene finds itself second to last on the leaderboard of the system analysis so far in this series. Here you can see the basic Lucene basic Lucene model workflow. The Lucene, as we know, is a powerful and efficient search engine that provides a vast range of text searching techniques as per your user requirements. Lucene is much more than any other text searching engine, as choices given to the user are not discriminators on any basis. It has powerful and strong searching algorithms that support a wide range of queries for searching. Lucene application have the basic cycle which primarily comprises of first indexing data, on which searching is the first indexing data on which the searching is performed at a specific path. The data added can be in any textual form as per user's needs. Data is indexed and tokenized, and then searching is performed on these tokens using queries. This is a two-way process, as it includes first processing of data and then searching on it. Component of Lucene. In order to use Lucene for text searching, let us take a close look at the main API used by Lucene. Please note that it is not a complete guide for the using. However, it will help you to get understanding of basic and radical Lucene API. Following is the API used to build Lucene based solution. The directory. It is the base class that defines where the indexes are performed. Document. It contains the data that is to be indexed. Analyzer. While the data is being indexed, the analyzer decided the criteria on the basis of which tokenizing and searching is done on data. Similarly, it is used while querying data, which also involve tokenization. Index writer. Documents which are created beforehand are passed to the directly using this class. One index writer can be opened at a time. Index reader. Every directory where the index are created may have readers open on it, which is responsible for reading data from the indexes. Index searcher. The search is responsible for querying the data through the readers. Directory. This class is a representation of the location where Lucene indexes are stored. A directory needs to be open for maintaining indexes so that the further operations can be performed on them. Document. Document is a collection of fields. These fields contain textual data as value assigned against a field name. The value is the data that you want to index, and then more searchable for future. With every field, a user can specify whether he wants to analyze that field value or not. Document is basically a unit of search which will be returned when the field is searched against searched item. Analyzer. Analyzer has the prime responsibility of tokenizing the data into a smaller chunk as per the type provided. It basically passes the field of the document into indexable tokens. The way of data being analyzed by the analyzer influences the user's ability to search data. There are 4 basic analyzers: white space analyzer, standard analyzer, simple analyzer, and stop analyzer. Index writer. In order to add document and index it, we need an index writer. The writer needs a valid Lucene directory where the document is to be indexed, and analyzer so that the writer analyzes the data according to it. Writer corresponds with the analyzer for the index data and then adds the result to the directory for storage of data. Precisely, the writer is responsible for all the write operations to be correctly performed on the data and then store it. There is a set of operations that can be performed on the writer. and the right is disposed after all operations. Index reader, the main functionality of Lucene is to search data added previously. For this purpose, we have the index reader, which reads the data from the directory. On every update in the documents, the index reader needs to be reinitialized. You can either create index reader or get an instance of index reader from index writer. You pass the directory instance to the reader, which has all the documents indexed. Index searcher is an initialized with the instance of index reader, which takes a query from the user and searches the data accordingly. A query is an abstract class provided by the Lucene's and is used to define scope and type of the searching to be performed. On searching, we are returned with the top docs, which is the result of searching with the query. Now that the query is created, you pass the query using the queryParser. Analyzer is passed to the queryParser, which passes the query according to that analyzer. Moreover, the field name is added to the document is passed to the query searcher so that the searches the data accordingly. An array is maintained in the top docs, which is known as score docs. Score docs will maintain the search result on a query execution basis. On iterating over this array, the resultant data can be retrieved. The recommendation the analyzer used for searching is recommended to be the same with the which the data was indexed at the first place. Here you can see a document in the raw form is connected to read content. Read content is connected to analyze document. Analyze document is connected to analyzer. Analyze is connected to index document. Index document is connected to index directory. Search content is connected to build query. Build query is connected to run query. Run query interacts with index directory, and run query is connected to get results. Here we are considering indexing and searching. This picture here shows two main processes, indexing and searching. The left hand side shows the indexing and the right hand side shows searching. Let's assume we have numerous documents and our application want to perform search. First step in doing so is indexing. Lucene can take huge number of documents as inputs. Internally building document object for its internal use, then analyzing these documents. Lucene then create tokens and from the document and ultimately create an index table of those documents. Once indexing is done, we are ready to search those documents. On the right hand side of this picture, we see users can search a specific term among millions of documents with relative easy. Here you can see raw content is connected to acquire content. Acquire content is connected to build document. Build document is connected to analyze document. Analyze document is connected to index document, and it is connected to index. Users is connected to search UI. Search UI is connected to build query. Build query is connected to run query. Run query interacts with the index. Run query is connected to render doc result. Render result is connected to search UI. Search UI here. You can see a sample Lucene index file in the project structure here. In this particular example, the index files will contain all text file which we want to index, and input file will contain the Lucene index document. We will search the index inside it, and this is specific arrangement in this project structure. Here you can see the Lucene example. Under that you can see the directories dot settings, index files, input source, input file, src, and target, and files .class, .project, and pom.xml. Here under source you can see main, and then Java, then com, and how to do in Java, then demo, and under demo you can see Lucene, and under that you can see the directories doc, file highlight, and you can also see under src main and test. This is a sample directory structure for a Lucene example here. Now we are focusing on search request. A program that received your search request compares it to the entries in the index and returns result to you. Here you can see run a query from your PishER inbox. The steps for this is one, navigate to your PishER inbox, and to enter your query string in the search bar in the top left corner of the page, and through the press enter key or return key on your keyboard. You can use Lucene to run queries in your PishER inbox or on the Pish RIP queries page. Here you can see query cache in action. Query cache provide query cache proves useful when you want to enable heavy query performance. Query cache defines an interface that allows caching queries at the junction when it is needed most at the start of the query. The query cache implementation used is LRU query cache. As the name implies, LRU query cache uses the least recently used algorithm to evict keys when the cache is full. Each query creates a wait instance associated with the corresponding index searcher. The default index searcher implementation uses an instance of LRU query cache to cache the incoming query and create the cacheable wait instance. When the scoring starts, the cacheable wait instance check whether the query is present in the cache. If it is present, the cache version is retrieved and returned. Otherwise, a cache load is done and the corresponding instance is returned. Query caches greatly speed up the performance under high load and repetitive queries. However, a large number of distinct query caches actually increase query latencies because of the additional query cache loading times. Also, if the query is being cached is large, that becomes significantly overhead in the entire query latency. The wait represent the pre-index search statistics associated with the query. This is essential because it allows a query to be reused as therefore, the same query can be used to access multiple index searches, but each index searcher will have its own wait instance. Remember that the wait is correlated to index searcher plus query, not just one of the two. When the query is given to an index searcher for execution, the index searcher instance creates a wait instance for the same. The lifetime of the wait is limited to the query execution lifetime within the index searcher. Wait is also responsible for participating in scoring process. Wait creates a corresponding scorer. The scorer Scorer is then invoked on various documents that the query is being evaluated against. Note that the weight is completely owned by the index searcher. It is only maintaining statistics for particular query, and the index searcher is free to play with the weight data as much as it wants, with no side effects impacting other parts of the system. Here the class index searcher implements search over a single index reader. Here the LRU class LRU query cache, the query cache that evicts queries using LRU least recently used eviction policy in order to remain under a given maximum size and number of bytes used. Here the index searcher is connected to a cacheable weight via create weight, and then cacheable weight is connected to a index searcher via instance. Then the score supply is given to cacheable weight, and cacheable weight is connected to LRU query cache via get. Then LRU query cache is connected to cacheable weight via object if cached, null otherwise. Then the cacheable weight is connected to is providing a cache object or the default version. Here you can see sample queries. Here the query application and sample query. Here for the term query application single term match. Here the sample query colon bar. Praise query, several terms coupled together. All cars with black tires. Here range query, ranged of here the in the term query the single term match. Here the praise query, the several terms coupled together. The range query, range of terms excluding or including the endpoints. Prefix matches given prefix. Fuzzy query, Lehmanstein algorithm for closeness matching. Wildcard query, regular expression like matching. Boolean query, multiple queries connected by logical clauses. As an example, we can consider this code segment. Here you can see the parameter query. The query string to be passed. Here the pass method and in this code here you can see now search the index here. Here pass a simple query that searches for the text here, and in this pass method this passes a query string and returning a query here. Now here we are considering terms in queryParser syntax in package org.apache.lucene.queryparser.classic. Single term is a single word such as test or hello. A praise is a group of words surrounded by double quotes such as here. Now we are considering fields. If you want to find a document entitled the right way, which contains the text don't go this way, you can enter this title right way and text go. You can search any field by typing the field name followed by a colon and then term you are looking for. As an example, let's assume the Lucene index contains two fields, title and text is the default field. Title and the text is the default field. If you want to find the document entitled the right way, which contains the text, don't go this way, you can enter this title the right way and text go, or here title the right way and go. Since the text is the default field, the field indicator is not required. Note the field is only valid for the terms that is directly proceed. So the query title the right way will only find the in the title field it will find right and way in the default field, in this case the text field. Now we are considering term modifiers. The wildcard searches to perform a single character wildcard search, use question mark symbol. To perform multiple character wildcard, use asterisk symbol. A single character wildcard search looks for the terms that match that the single character replaced. For example, to search for text or test, you can use search here. Multiple character wildcard searches look for 0 or more characters. For example, to search test or tester, you can use the search test asterisk. You can also use the wildcard searches in the middle of a term, t asterisk t. The note, you cannot use asterisk or question mark symbol as the first character of a search. Now we are considering or in Boolean operators. To search search for documents that contains either Jakarta Apache or just Jakarta, use the query here. Or you can use Jakarta Apache or Jakarta. Now we are considering grouping. To search for either Jakarta or Apache and website, use the query here. This eliminates any confusion and make sure make sure that website must exist and either term Jakarta, Apache, Jakarta or Apache may exist. Now we are considering field grouping. To search for a title that contains both the word return and the phrase Pink Panther, use the query here. Now we are considering escaping special characters. To escape this character, use the backward slash before the character. For example, to search for 1 plus 1, open curly brace, 1 plus 1 closing open bracket, 1 plus 1 close bracket and colon 2, use the query here. As an error example, we can consider this one: unable to get the list of search result, unable to process the search request, and invalid search query, and out and repository ID colon TCM, and organizational item ancestor IDs colon TCM, etc. And here you can see org.apache.lucene.search.boolean query $, too many clauses, etc. And now we are focusing on Lucene queryParser. queryParser API. This module provides a number of query parsers: flexible query parser, classic query parser, complex phrase query parser, extendable query parser, surround query parser, span queries, query parser building query object from XML. If you are new to query parsers, a flexible query parser's standard query parser is probably a good place to start. Here you can see the control flow of query process. With linear scan, linear scan is a simple process of sequentially going through each line of the system and checking for the parameter, that is condition given in the query. This is precisely how Unix grep command works, and it also more fairly well with the wildcards and regular expressions. If the size of data set being search size is not too large and the hardware being used reasonably powerful, linear search is the simplest way. However, linear search start showing the performance degradations beyond a medium size document. The world around us is too experiencing an information explosion. In fact, the amount of data that needs to process to extract information has quadrupled over at least 10 years, thanks to the advent of connected world, handheld devices and IoT. Linear search cannot scale to meet those needs, so we need something more sophisticated and performant that can handle massive dataset while still providing relevant results at reasonable speed. Linear searches also limit what kind of queries can be answered. For example, there is no way to define query that seeks close matches of the given pattern. Suppose an instance that we search for document with the words flower and sunshine within proximity of 3 words in a document. Doing so with linear search is impossible. Also, there is no notion of ranked result. That is, given a query, a result is either a match or not for a linear scan. If we want some sort of ranking, we cannot use this linear scan. The inverted index is a data structure used to store data in an inverted manner, that the terms are mapped to a document in which the terms appear. Any unique term appearing in any document is made a part of the inverted index. To create an inverted index, the fields within the document are first split and tokenized. A shorted list of all unique terms are created, and the documents that contain corresponding terms are populated. While being fast for single term query, inverted indexes are also answer an important class of questions, similarity queries. This figure shows the typical way a query is processed in IR systems, information retrieval systems. A query comes in and is passed and is split into individual tokens. Token is an independent term having its own semantics in a query. For example, consider the following query: find all people who drove to college yesterday. In this scenario, tokenizing the query will lead to the independent terms such as drove, college, yesterday, and to. Stop list. Stop list consists of words that are used in the associated language to form the structure of sentences, but are not necessarily useful for semantics matching and searching. For example, in sentence Alex went to London, we see that the word to is a stop word because that helps form a structure of the query. However, it cannot necessarily contribute anything to semantic assessment of the potential document match, and so it should not be considered on the same lines. Stop words are filtered out before further processing to help limit the number of tokens in the index to ones that can contribute to the relevant document. Of course, later on we might discover some of the semantically able words are not useful in matching a relevant document, but that is done stage by stage. Stemming. Queries can contain words in the different forms with different tenses, spelling, and associated grammatical semantics. For example, drive, drive-in, drives are all based on the same word but differ in their structure. However, for semantics matching, the actual structure of the word is of little value. What really matters is the root word, which will contribute to calculate the overall relevance of a document to the query. Another advantage of discounting different structure of the same word is to allow the one to match the remaining. For example, query containing the word drive should match document containing the word driving. This increases the recall of the query result. Recall is defined by a breadth of the returned result, that is how many documents match a given query. Unlike the relational database, IR systems can answer queries with the semantic element with them. That is, any document can match the given query. The trick is to identify most relevant ones and eliminate the unnecessary noise. Recall is the width of a document and return result. However, too high a recall and return result will have lower correctness. Too low a recall and return results are very small in size. Most IR systems struggle with this trade-off. Stemming is the process of reducing words to their base word and removing structural differences between words that originate from the same root. However, stemming can be crude in the operations. For example, stemming can employ a crude heuristic to remove parts of the word which can sometimes lead to weird semantic outputs. While this is efficient and works most of the time, the more sophisticated way to deal with this requirement is the art of lemmatization, rewriting words using a given vocabulary and depending on morphological analysis of the tokens of the query. Lemmatization is beyond the scope of current discussion. To avoid linear search, you can index the set of document in advance and use special queries to get the right set of results. Consider, for example, set of document with the range of word present. Let's use a group of related books shown. Books database in action world of Lucene introduction to information retrieval. Let us assume that we have to serve queries across all three of these books. Doing so requires what we index data across all three books so that we can efficient in query operations. Note that there are multiple ways to do same thing. We can create a separate index per book or index all three books in the same index. Note that these books will have the same key terms in common. For example, except search to be present across all three of the text. Similarly, bytes is another term that can repeat across all three texts. The naive indexing technique is to maintain independent metadata about each of the document, effectively discarding the common terms present. This method is a waste of space and is inefficient for serving queries that seek matches across all text. To implement inverted indexes, you first need to understand concept of term and the term document incident. So a term document incident matrix. Here you can see queries connected to query tokens via pass query. Query tokens tokens are connected to stop list via filtering. Stop list is connected to stemming. Stemming is connected to index, and index is connected to retrieved. Index is connected to Boolean or similarity query via retrieve relevant document set, and Boolean or similarity query is connected to rank index via ranking. As an example, we can consider org.apache.lucene.queryParser.classic package. A simple query parser implemented with Java CC. As an example too, we can consider this code segment. Here the query parser, class query parser. This class is generated by Java CC. The most important method is query parser base dot parse string. The syntax for query strings is as follows. A query string is a series of clauses. A clause may be preceded by a plus or minus sign indicating that the clause is required or prohibited respectively, or a term followed by a semicolon followed by a colon indicating the field is to be searched. This enables one to construct queries which search multiple fields. A clause may be either a term indicating all the documents that contain this term, or a nested query enclosing in parentheses. Note that this may be used with plus or minus prefix to require any of a set of terms. Thus the BNF, the query grammar is query here equals clause asterisk, clause equals here plus and minus, then term dot and within brackets a term or query. This is in the package org.apache.lucene.queryparser.classic. Here in this construct, this create a query parser, and this is string f, the default field for query terms, and this is the analyzer used to find terms in the query text. In this parse method, this is the parses a query string and returning a query. The parameter is string query here, the query string to be passed. As an example 3, we can consider org.apache.lucene.queryparser.flexible.standard.config package, a standard Lucene query configuration. The package org.apache.lucene.queryparser.standard.config contains a Lucene query configuration handler, standard query config handler. This configuration handler reproduces almost everything that could be set on the old query parser. This is about standard query Lucene, standard Lucene query configuration. Now we are considering Lucene 9.7.0 query parser API. Apache Lucene, the Apache Lucene the query parsers. This module provides a number of query parsers: flexible query parser, classical query parser, complex trace query parser, extensible query parser, surround query parser, span queries, query parser building query object from XML. If you are new to query parsers, the flexible query parser, standard query parser is probably a good place to start. Now we are considering standard syntax, class standard syntax parser in package org.apache.lucene.queryparser.flexible.standard the parser for the standard Lucene syntax. Now we are considering query parser, class query parser in package org.apache.lucene.queryparser.classic. This class is generated by Java CC. The most important method is queryParser base.parse string. This syntax for query string is as follows. The query is series of clauses. Clause may be prefixed by plus or minus sign, indicating that the clause is required or prohibited respectively, or term followed by a colon indicating the field to be searched. This enable one to construct queries which search multiple fields. Now we are considering class complex praise queryParser. In package Apache lucene.queryparser.complex praise queryParser, which permits the complex praise query syntax. For example, this one, the Jonathan title mark and Peter's asterisk here. Now we are considering extendable queryParser. Class extendable queryParser in package Apache lucene.queryparser.ext. The extendable queryParser enables arbitrary queryParser extension based on the customizable field naming scheme. The Lucene syntax allows implicit and explicit field definition as query prefixed followed by a colon character. Extensible queryParser allows to encode extension keys into the field symbol associated with the registered instance of parsed extension. A customizable separation character separates the extension key from the actual field symbol. The extensible queryParser split the extension key from the field symbol and tries to resolve the associated parse extension. If the parser can't resolve the key, or the field token does not contain the separation character, extensible queryParser yield the same behavior as if the superclass queryParser. Otherwise, if the key is associated with the parse extension instance, the parser builds an instance of extension query to be processed by the parse extension.parse extension query. If the extension field does not contain the field part, the default field for the query will be used. Now we are considering class queryParser in package Apache.lucene.queryparser.surround.parser. This class is generated by Java CC. The only method that client should need to call is parse method. Now we are considering class coparser in package Apache.lucene.queryparser.xml. Assembles a query builder which uses only core Lucene query objects. Now we are considering overview in queryParser syntax. In package Apache.lucene.queryparser in .classic. Before choosing to use the provided queryParser, please consider the following here. Although the Lucene provides the ability to create your own queries through its API, it also provides a rich query language through the queryParser, a lexer which interprets the string into a Lucene query using Java CC. Generally, the queryParser syntax may change from release to release. This page here we describe the syntax as of the current release. If you are using a different version of Lucene, please consult the copy of the docs or queryParser syntax .html that was distributed within the version you are using. Before choosing to use provided queryParser, please consider the following. If you are programmatically generating a query string and then passing it with the queryParser, then you should seriously consider building your queries directly with your query API. In other words, queryParser is designed for human entered text, not for program generated text. To the tokenized field are best. Untokenized fields are best added directly to queries and not through the queryParser. If a field's values are generated programmatically by the application, then so should query clauses for this field. The analyzer which the queryParser uses is designed to convert human entered text to return terms. Program generated values like dates, keywords, etc. should be consistently program generated. 3. In a query form, fields which are generated text should be used the queryParser. All others such as date ranges, keywords, etc. are better added directly through the query API. A field with a limit set of values that can be specified with the pull down menu should not be added to the query string which is subsequently passed, but rather added as a term query clause. Now we are considering terms. A query is broken up into terms and operations. The class terms in package Apache.lucene.index access to the terms in a specific field. There are two types of terms: single terms and phrases. Multiple terms can be combined together with Boolean operators to form a more complex query. Note that the analyzer used to create the index will be used on terms and prices in the query string. So it is important to choose an analyzer that will not interfere with the terms used in the query string. Now we are considering fields. The Lucene supports field data. The class field in package Apache.lucene.index provides the term index for fields that have it and list which fields to. This is primarily an internal experimental arrangement by API, although it is used to expose the set of term vectors per document. Lucene supports fielded data. When performing a search, you can either specify a field or use the field default field. Field names and default fields is implementation specific. We are considering term modifiers. Lucene supports modifying query terms to provide a wide range of searching options. Wildcard searches, regular expression searches, fuzzy searches, proximity searches, range searches, boosting of term. Now we're considering Boolean operations. Boolean operations allow terms to be combined through a logic operations. Lucene support and, plus, or, not, and dash as Boolean operators. Not Boolean operators must be all caps. Now we are considering grouping. Lucene supports using parentheses to group clause to form subqueries. This can be very useful if you want to control the Boolean logic for a query. Now we are considering field grouping. Lucene supports using parentheses to group multiple clauses to a single field. Escaping special characters. Lucene supports escaping special characters that are part of the query syntax. The current list of special characters are plus, minus, ampersand, two or symbols, and blank sign, and or not sign, and open bracket, close bracket, open curly brace, close curly brace, open square bracket, close square bracket, caret and double quotation, title, asterisk, question mark, colon, backward slash, and forward slash. To escape this character, use the backward slash before the character. In exception example, we can consider pass exception, the class pass exception. This exception is thrown when pass errors are encountered. You can explicitly create objects of this exception type by calling the method generate pass exception in the generated parser. You can modify this class to customize your error reporting mechanisms. So long as you retain the public fields. This is in package org.apache.lucene.queryparser.classic. As an error example, we can consider this occurred in Confluence. Invalid syntax cannot pass, syntax error cannot pass, equal at the com.altasian.confluence.search.v2.lucene.mapper.abstract text field query mapper dot try parse, abstract text field query mapper dot java. Course binary syntax cannot pass, syntax error cannot pass equal at apache dot org.apache dot lucene dot queryParser dot flexible dot standard dot parser dot standard syntax parser dot generate parse exception standard syntax parser dot java. Now we are focusing on external interface. Now we are focusing on Lucene searcher. org.apache.lucene.search provides data structures to represent queries, that is term query for individual words, phrase query for phrases, and boolean query for boolean combination of queries, and the index searcher which turns queries into top docs. A number of query parsers are provided for producing query structures from strings or XML. Here you can see Lucene searching mechanism. As shown in this figure, the query string requested by the user will be passed by the queryParser class in the beginning. Not only just pass the string into the corresponding query object for searching, but also tokenize every word of the indexes using the particular analyzer that is the same as the one during the indexing process. Finally, search the build index. Finally, search the build index files for query results, which will be encapsulated in TopDocs class and return back to users. Here user is connected to query string. Query string is connected to queryParser and analyzer, which has queryParser and language analyzer. queryParser is connected to language analyzer. queryParser and analyzer is connected to index files. Index files are connected to return search results. Return search results are connected to documents, and documents are connected to show results to user, and show results to user is connected to user. Here you can see indexing and search. Apache Lucene is an open source Java-based indexing and search technology. It is a technology suitable for any application that requires full text search, especially cross-platform. Lucene works by first indexing the data to be searched, and then using index for searching. Indexing is the process of converting text data into a format that facilitates rapid searching. Lucene stores the data in the form of inverted index. An analogy is an index at the end of a book, and index points to the location of topics that appear in the book. There will be terms created from the input which point to the documents. Terms are indexed, and any search is performed on terms, and related documents are fetched. Lucene index is built over an implementation of the directory class. Lucene supports multiple directory implementation. RAM directory, complete index is kept in the memory. FS directory, complete index is stored in the file system. NIO FS directory supports multiple threads on fs directory. Terms to be created for indexing can be governed by something called analyzers. The analysis, the input to be indexed can be analyzed to extract the terms on which the searching can be done, like extracting word, removing common words and changing the words to lowercase, etc. Analyzers are used to, both at indexing time and searching time. It is highly recommended to use same analyzers both at index creation and searching time, so that tokens created for searching are created in the same way that the data is indexed. Analyzers internally use tokenizers and filters. Analyzers can take a string as input and returns back to the stream of tokens. Lucene provides some out-of-box analyzers which come handy. In addition to custom analysis can also be created. Some analyzers are simple analysis, analyzer, white space analyzer, n-gram filters, n-gram token filter, h n-gram token filter, length filter. Adding data to an index. Lucene index comprises document which contain fields. Field represent a piece of data queried and retrieved in a search. Field class encapsulate the field name and its value. Lucene provides options to specify if a field needs to be indexed or analyzed, if its value needs to be stored. Field contains terms which are used for querying. Each field has semantics about how it is created and stored, that is tokenized, untokenized, raw data, compressed, etc. Document represent a collection of all fields. Term point to documents. The data that needs to be retrieved through searching needs to be stored in a form of document. Index writer, the class that either creates or maintains an index. Its constructor accepts boolean that can determine whether a new index is created or whether the existing index is open. Document deletion. Lucene provides an index read abstract class that contains methods for deleting documents from an index. Lucene internally refers to document with the document numbers that can change as documents added or deleted from the index. Lucene index optimization. The index optimization is a process to merge all segments to present to an index into a line segment. Optimizing an index is recommended since it improves the search response time. Optimization of index should be done just before closing the index writer. Lucene searching and retrieval. Searching is the process of finding matching document for the input. For the input text. The input text is processed through a chain of analyzers to generate set of terms to be queried. The terms generated from the analysis are used in the query. Lucene search generates a score which is generated using combination of the vector space model VSM of information retrieval and the Boolean model to determine how relevant a given document is to a user's query. Here you can see index in the left side and searching in the right side. Here they are in indexing. it's connected to extract text data, and extract text data is connected to analysis. Analysis is connected to the index tokens, and index tokens are connected to Lucene index. Here the extract text data analysis and index tokens are in indexing here. In searching, pass search string and analysis, and create search Lucene query, search index and Lucene index, and retrieve search result, and display results are in searching. And here the pass search string analysis, index tokens, and create Lucene query, search index, Lucene index, and retrieve search index are inside are in Lucene API. Here searching is connected to a pass search string, and pass search string is connected to analysis. Analysis is connected to create Lucene query. Create Lucene query is connected to search index. Search index is connected to Lucene index. Lucene index is connected to retrieve search result. Retrieve search result is connected to display result, and provided the result. Here you can see a basic search application. A lot of application may choose to go for other search integration solutions like Apache Solr, Elasticsearch, which are built on top of Lucene, or just opting to use NoSQL databases like MongoDB, Cassandra. However, Apache Lucene over its alternative one, the Java ecosystem integration. If your project is built using Java or integrates with Java, Lucene's integration within the Java ecosystem can be an advantage to granular control. Lucene allows you to control various aspects of indexing and searching, making it suitable for complex use cases. Indexing and searching performance. Lucene, being a low-level solution, is known for its indexing and searching performance, making it a solid choice for projects that require efficient search operations. Ranking control. For ranking control, Lucene provides a high level of control over ranking of search results and what should be shown to other users. If an application faces this requirement, you may opt to go to Apache Lucene as their search solution. In fact, for those of you who want Samsung phone, the search on your device is powered by Lucene. The two main steps involved in search application which Lucene library provides support for are indexing. First one, indexing the document in searchable format. Two, parsing the search query and returning the relevant result. Indexing to search large amount of text quickly, you must first index the text and convert it to a format that will let you search in rapidly, eliminating the slow sequential scanning process. This conversion process is called indexing. And its output is called an index. Most such applications use inverted index. The inverted index is designed to facilitate efficient keyword-based searches by storing the mapping of the terms to the document where they apply. The core Lucene classes for indexing. Document. The document class is a Lucene context, refers to the searchable object we want to search for in our search application. Document is a container for various fields. The field class represents the specific attribute or piece of information associated with the document which we want to index and make searchable. It consists of a key value pair, field name, and the content we want to index. Index writer. The index writer class acts as a core component which create and update indexes during the indexing process. Analyzer. The analyzer class is responsible to analyze the document and get the tokens and words from the text which is to be indexed. Directory, the directory class represents the storage location of the indexes on your disk. Searching with Lucene, when you search in Lucene, you formulate queries that target a specific field or a combination of fields. Lucene, in order to index, efficiently point to the documents that match your query terms, allowing for fast retrieval of relevant documents. The core Lucene classes for searching, the index searcher. The index searcher class acts as a core component which reads searches index created after the indexing process. Field, the field class is the lowest unit of searching. It is similar to field indexing process. Query, the query class is an abstract class and contains various utility methods and is the parent of all types of queries that Lucene uses during search process. Term query, the term query class is the most commonly used query object and is the foundation of many complex queries that Lucene can make use of it. Top docs point to the top end search result which matches the search criteria. queryParser, the Lucene queryParser utility. queryParser is a utility class that allows you to construct queries using user-friendly query syntax. In Apache Lucene, the analyzer is a critical component used for text processing during both indexing and searching. It's responsible for breaking down text into individual terms, tokens, normalizing those terms, and applying optional transformations like stemming or removing stop words. Here you can see the raw content is connected to acquire content. Acquire content is going to build document. Build document is going to do an analyze document. Analyze document is going to index document. Index document is going to index. And here users are connected to search user interface. Search user interface is connected to build query. Build query is connected to run query. Run query is connected to interacts with index. Run query is connected to render result. Render result is connected to search user interface. Here the search user interface, build query, run query, and index and render result, and acquire content, build document, analyze document, index document, and index document in administration into between in the level of administration interface and analytic interface. Here you can see a simple searching process. With the searching with Lucene, when you search in Lucene, you formulate queries that target the specific field or combination of fields. Lucene inverted index efficiently point to the document that match your query terms, allowing for fast retrieval of relevant documents. The core Lucene classes for searching is index searcher. The index searcher class acts as a core component which reads and searches index created such indexes created after the indexing process. Field the field class is the lowest unit of searching. It is similar to field in indexing process. Query, the query class is an abstract class that contains various utility methods and is the parent of all types of queries that Lucene uses during searching process. Term query, the term query class is the most commonly used query object and is the foundation of many complex queries that Lucene can make use of. Top docs point to the top end search results which matches the search criteria. queryParser, the Lucene queryParser is the utility that allows you to construct queries using user-friendly syntax. Here the class analyzer. The analyzer builds token streams in the package org.apache.analysis and the analyzer builds a token stream which analyzes text. It thus represents a policy for extracting index terms from text. Class index searcher implements search over a single index reader. Class index reader an abstract class providing an interface for accessing a point in time view of an index. This is the package org.apache.lucene.index. Any changes made in the index via index writer will not be visible until a new index reader is open. It's best to use with directory reader.open index writer to obtain an index reader. If your index writer is in process, when you need to reopen and to see changes in index, it's best to use directory reader.open if change directory reader, since the new reader will share the resources with the previous one when possible. Search of an index is done entirely through this abstract interface, so that any subclass which implement it is searchable. Class directory in package org.apache.lucene.sto. A directory provides an abstract layer for storing a list of files. A directory contains only files, no subfolder hierarchy. A class topdocs in org.apache.lucene.search represent hits returned by index.indexSearcher .search query int. Here the expression is connected to queryParser. queryParser interacts with the analyzer via text fragment, and queryParser is connected to indexSearcher via query object. IndexSearcher is connected to index reader, and indexReader is connected to directory. And here the indexed search is connected to topdocs. Now we are considering VCM score in the TF IDF similarity defines the component of Lucene scoring. Overriding computation of this component is convenient way to alter Lucene scoring, suggesting here we are discussing how Lucene scoring evolves from underlying information retrieval models to efficient implementation. We are considering on VSM score. Lucene combines Boolean model BM of information retrieval with the vector space model VSM of information retrieval. The documents approved by BM are scored by VSM. In VSM documents and queries, documents and queries are represented in weighted vectors in a multidimensional space where each distinct index term is a dimension. The weights are in TF IDF values. VSM does not require weights to be TF IDF values, but TF IDF values are believed to produce search result of high quality, and so Lucene is used TF IDF TF and IDF are described in more. I'm going to describe in more details now. But for now, the compilation, let's just say that given term T and the document or query X, TF function T comma X varies with the number of occurrence of the term T in X. When one increases, so does the other. And the IDF function, the parameter T, similarly varies with the inverse of the number of index document containing term T. VCM is score is of document D for query Q is a cosine similarity of the weighted query vectors VQ and VD here, where VQ and VD dot VD is the dot product of weighted vectors, and here the absolute VQ and here the absolute V are the Euclidean norms here, two norms. Note the above here, this equation can be viewed as a dot product of the normalized weighted vectors, in the sense that the dividing VQ by its Euclidean norm is normalizing it to a unit vector. The normalizing normalizing VD to the unit vector is known to be problematic in that it removes all document length information. For some documents, removing this info is probably okay. For example, document made by duplicating certain paragraph 10 times, especially if that paragraph is made of distinct terms. But for the document contain no duplicated paragraph, this might be wrong. To avoid this problem, a different document length normalization factor is used, which normalizes to a vector equal to or larger than the unit vector doc length norm D. At indexing, users here you can see formatting only and the cosine similarity formula here. Now we are considering Lucene conceptual scoring formula. The Lucene refines VSM score for both search quality and usability. Normalizing VD to the unit vector is known to be problematic. That removes all document length information. For some document, removing this info is probably okay. For example, document made by duplicating a certain paragraph 10 times, especially if that paragraph is made of distinct terms. But for the document which contains no duplicated paragraph, this might be wrong. To avoid this problem, different document length normalization factor is used. This which normalizes to a vector equal to or larger than the unit vector doc length norm D. At indexing, users can specify certain document are more important than others by assigning a document boost. For this, the score of each document is also multiplied by its boost value, doc boost D. Lucene is field based, hence each query terms apply to a single field. Document length normalization is by the length of the certain field. In addition to the document boost, there are also document field boost. The same field can be added to a document during the indexing several times, and so the boost of that field is a multiplication of boosts of the separate parts of addition, so part of the field within the document. At search time, users can specify boost to each query, subquery, and each query term. Hence, the contribution of a query term to the score of a document is multiplied by the boost of that query term, query boost Q. The document may match the multi-term query without containing all terms of that query. So this is the correct for some of the queries. Under simplifying assumption of a single field in the index, we get Lucene conceptual scoring formula here. The conceptual formula is a simplification in the sense that one terms and the documents are fielded, and the two boosts are usually per query term rather than per query. Now we describe how Lucene implement this conceptual scoring formula and derive the Lucene's practical scoring function. For efficient score, for efficient score computation, some scoring components are computed and aggregated in advance. Query boost. For the query, actually, for each query term is known when search starts. Query Euclidean norm can be computed when the search starts, and it is independent of the query being scored. From search optimization perspective, it is valid question why bother to normalize the query at all, because all scored documents will be multiplied by the same query Euclidean norm, and hence the documents ranks, their order by score will not be affected by this normalization. There are two good reasons to keep this normalization. Recall the cosine similarity can be used to find how similar two documents are. One can use Lucene for example, clustering, and use a document as a query to compute its similarity to other documents. In this use case, it is important that the score document D2, D3 for query D1 is comparable to the score of document D3 for query D2. In other words, the score of document two distinct queries should be comparable. There are other applications that may require this, and this is exactly what normalizing the query vector VQ provides. Comparability to a certain context extent of two or more queries. Document length norm, doc length norm D, and the document boost, doc boost D, are known at indexing time. They are computed in advance, and their multiplication is saved as a single value of in the index. Norm D, index norm D, in the equations in the index norm D. Here you can see a Lucene conceptual scoring formula. Now we are considering Lucene practical scoring function. The document length norm, doc length norm, and the document boost, doc boost D, are known for at indexing time. They are computed in advance, and their multiplication is saved as a single value in the index norm D. Sorry, norm D is not here. In the equations here, the norm T in D means norm field T in doc D, where field T is the field associated with the term T. Lucene's practical scoring function is derived. The color codes demonstrate how it relates to those of the conceptual formula, where TF T in D correlates to terms frequency, defined as a number of times terms T appeared in the currently scored document. Documents that have more occurrences of a given term received a higher score. Note that TF T in Q is assumed to be 1, and therefore it does not appear in this equation. However, if the query contains twice the same term, there will be two term queries with that same term, hence the computation would still be correct, although not very efficient. The default computation for TF T in D in classic similarity is term frequency computation. TFT in D equal frequency to the power half. IDF T stand for inverse document frequency. This value correlates to the inverse of doc freq, the number of documents in which the T time T appears. This means rarer terms gives higher contribution to the total score. IDF T appears in T both in the query and the document. Hence it is squared in the equation. The default computation for IDF T in classic similarity is IDF T equal 1 plus log inverse document frequency computation doc min plus 1 divided by doc freq plus 1. Sorry, doc 1 plus log as parameters function arguments as doc, sorry, 1 plus doc open curly brace doc count plus divided by doc freq plus 1 close curly brace. T dot get boost is a search time boost of term T in the query queue as specified in the query text, or as set by wrapping the query boost with boost query. Notice that there is really no direct API for accessing a boost of one term in multi-term query, but rather multi-terms are represented in a query as multi-term query object, and so the boost of a term is query is accessible by calling subquery getBoost method. Norm TD is an index time boost factor that slowly depend on the number of tokens of the field in the document, so that shorter field contribute more to the score. So here you can see the Lucene conceptual scoring formula. Here you can see a scorer in a search. Scorer is a core of the search process in Lucene. Scorer is responsible for identifying matches and scoring hits from set of documents present. Scorer is a special class. It is also an extension of a class known as docID set iterator. docID set iterator allows iteration over document IDs, thus allowing seek over the index to get a specific document or to iterate over all documents. Note that the iterator can go forward only. It cannot go backward. This restriction simplifies the underlying codex supporting the iterator. docID set iterator provides three useful methods. docID method get the internal index document ID for this document. This method always returns monotonically increasing document IDs. Next doc method iterate to the next doc and advance to the location specified. This interface allows the scorer to iterate over all documents and determine whether they are relevant to the query. The scorer works by implementing scorer method on top of iterations. The score method gets the current document ID and gets the current document and returns the score for the same. The index reader has statistic about the current document that can be fully utilized by the scorer to determine the score. If terms vectors are enabled for the field, the scorer can get access the index reader is here. The index reader has statistic about current document that can be fully utilized by the scorer to determine the score. If the term vectors are enabled for the field, and the scorer get access to the term vector and perform even more elaborate operations. How scoring is performed, here you will see how it all fit together. The user issues a query with the instance of a query class. Query is given by given to an index searcher, which first rewrite the query recursively, invoking any modification or simplification is possible. Upon completion of the rewrite, the instance of the wait class is created, which is specific to the query plus index searcher combination. This wait will contain all the query specific statistics that apply to the execution of this query. During the scoring, the wait creates a scorer which iterates over all documents in the index, filters out the irrelevant document, and applied the scoring algorithm on the candidate documents. The scoring algorithm can be anything that the user chooses to implement or use, but typically is a version of terms, frequency, inverse document, frequency, TF, IDF family. Score interacts with the index reader to get relevant details from the underlying file directory. If a term vector is present, the scorer can choose to use features from that as well as calculate scorer for the document. Scorer is expected to return a score per document it iterates on. After scoring completes, the results are returned to a collector, which then chooses the next set of steps. If the top n hits are requested, the collector typically will remain in a priority queue to identify top n hits and then return them back to the user. Here the class query in package org.lucene.search, abstract base class for queries. Class index searcher implements search over a single index reader. Class weight, the expert the calculate query weights and build query scorers. Class scorer, expert common scoring functionality for different types of queries. A scorer exposes an iterator method over documents matching a query in increasing order of the doc ID. Class index reader in package org.index. Index reader is an abstract class providing an interface for accessing a point-in-time view of an index. Interface collector in org.lucene.search. The collectors are primarily meant to be used to gather raw results from search and implement scoring or custom filtering, collation, etc. Lucene score collectors are derived from the collector and simple collector. Here you can see the query. Then query is connected to search index searcher. Index search is connected to weight. Weight is connected to score. Score interacts with index reader, and score is connected to collector. As an example, we can consider org.apache.lucene.search package, code to search indices. As an example too, we can consider this code segment. Here the index searcher, class index searcher, implements search over a single index reader. And here you can see the method public top docs search query int n finds the top n hits find the top n hits for query, and this is this index searcher is in package org.apache.lucene.search. Here the field score docs the top hits for the query. Here the score docs here the class store docs holds one hit in top docs. Here the query, the abstract base class for queries. In this code you can see this now search the index here. And here pass a simple query that searches for text. We can consider this code segment for example 3, and here you can see the class query, the abstract class base class for queries, and this class is in package org.apache.lucene.search. Here you can see term query, a query, the class term query here, a query that matches documents containing a term. This may be combined with other terms with a Boolean query. Here with this constructor, this constructs a query for the term here. Here you can see praise query. A query that matches documents containing a particular sequence of terms here. A praise query is built by queryParser for input like New York. Here is this constructor, an empty praise query, and the here with the add set term to end of the query praise, and this example is valid for Lucene 4.7.0. If you are using, for example, Lucene 9, you have to replace this code segment with praise query.builder. Here you can see a Boolean query, a query that matches the document matching Boolean combination of other queries. Here this constructor construct an empty boolean query with here the adds a clause to a boolean query. Here the enum boolean clause dot occur. Here occur must use this operator to close for clauses that must appear in the matching document, and in here should use this operator for clauses that should appear in the matching documents, and must not use this operator for clauses that must not appear in the matching documents. This again, this code is valid for Lucene 4.7.0. If you are using Lucene, for example, 9, replace this code segment with boolean query.builder. Here in this code we can consider integrating field values into the score. The this query matches the same document as original query, and computes the scores as similarity plus 0.7 multiplied by feature score. Here the boolean query, a query that matches documents matching boolean combinations of other queries. For example, term queries, price queries, or other boolean queries. Here the class builder, boolean query.builder, a builder for boolean queries. The constructor is a sole constructor. Here with the add method, add a new clause to this boolean query.builder. Here you can see the enum boolean clause.occur. Here the enum constant should use this operator for clauses that should appear in the matching documents. Here in the term query, a query that matches the documents containing the term. This may be combined with other terms with a boolean query. The construct boolean query construct term query term. Here construct a query for the term here. Here the method build creates a new boolean query based on the parameters that have been set in the this builder. Here you can see a feature field. This is a field that can be used to store static scoring factors into documents here. Here the new saturation query, this returns a new query that will score document as weight as one float, and a reasonably good default pivot value is computed based on the index statistics and is approximately equal to the geometric mean of all values that exist in the index here. This is field name and this is feature name. These are belongs to these are in a different package. Actually, it's in Lucene document. Here you can see the class boost query. A query wrapper that allows to give a boost to the wrapped query. Boost values that are less than 1 will give less importance to this query compared to other ones, while values that are greater than 1 will give a more importance to the scores returned by this query. Here you can see the constructor wrap query in such a way that the produced scores will be boosted by here the boost. This is the query and this is the boost. And here you can see the query builder, boolean query dot builder. Here is add and the build is there. While similarities help score a document relatively to a query, it is also common for documents to hold features that measure the quality of a match. Such features are best integrated into the score by indexing a feature field with the document at index time, and then combining the similarity score and the feature score using a linear combination. Here the query matches the same document as original query and computes scores as similarity score plus 0.7 multiplied by feature score. In this example, you can see integrating field values into a score. In this example, shows how to compute scores as similarity score multiplied by math.log popularity using expressions module. And assuming that values for the popularity field have been set in numeric in a numeric doc values field at the index time. Here the sort field stores information about how to sort documents by terms in an individual field. Fields must be indexed in order to sort by them. Here in the constructor creates a sort by terms in a given field with the type of return type of term values explicitly given. Here short field dot type dot score, and here you can see int, and here you can see compile an expression. Here you can see symbol bindings just maps variables to short field instances. Here create a query that matches based on the original query, but scores using expression. The less efficient yet more flexible way of modifying scores is to index scoring features into doc value fields and then combine them with the similarity score using function score query. From the queries module. For instance, this example shows how to compute scores as similarity score multiplied by math.log popularity using expressions module and assuming that values for the popularity field have been set to a numeric doc values field at the index time. As an now we are considering search basics in package Lucene.search. To perform a search, application usually called indexsearch.search query int. The public top docs search query int n find the top n hits for a query. This is in the class index searcher, implements search over a single index reader, and in the package Lucene.search. Lucene offers a wide variety of query implementations, most of which are in this in the package of Apache.Lucene.search or the queries module. These implementations can be combined in a wide variety of ways to provide complex querying capabilities along with the information about where the matches took place in the document collection. The query class section highlights some of the more important query classes. To perform a search, applications usually call indexreader.search query int. Once query has been created and submitted to an index searcher, the scoring process begins. After some infrastructure setup, the control finally passes to the weight implementation and its scorer or bulk scorer instances. Now we are considering term query in query classes. Constructing a term query is as simple as this, and the class term query in package Lucene.search a query that matches document containing a term. This may be combined with other terms with the Boolean query. Of the various implementation of query, the term query is the easiest to understand and the most often used in applications. The term query matches all the documents that contain specific term, which is a word that occurs in a certain field. Thus, the term code identifies and scores all documents that have the field with that have a field with the specified string in it. Constructing a term query is as simple as this. In this example, the query identifies all documents that have the field named field name and containing the word term. There are the query classes: Boolean query, point range query, fuzzy query. Now we are considering scoring. The introduction in scoring. Lucene scoring supports a number of pluggable information retrieval models, including these. Lucene scoring is a heart of why we all love Lucene. It's blazingly fast and it hides almost all of the complexity from the user. In a nutshell, it works. At least that is until it doesn't work, or doesn't work as one would expect it to work. Then we are left digging into Lucene internals and asking for help in java-user at lucene.apache.org to figure out why the document of five of our query terms score lower than the different document with only one of the query terms. While this document won't answer your specific scoring issues, it will hopefully point you to the places that can help you figure out what and why Lucene is scoring. You can contact the for the help java-user at lucene.apache.org. Lucene scoring supports a number of pluggable information retrieval models, including vector space model, VSM, probabilistic models such as Okapi, BM25 and DFR, language models. These models can be plugged in via Similarity API and offer extension hooks and parameters for running. In general, Lucene first finds the document that need to be scored based on the Boolean logic in the query specification, and then rank this subset of matching documents via retrieval model. For some valuable references on VSM and IR, in general refer to the Lucene wiki IR references. Now we are considering scoring basics. To be sure to use the useful index searcher.explain query doc to understand how the score for a certain matching document was computed. The method public explanation explain query int doc returns an explanation that describes how doc scored against query in class index is in the class index reader in the package apache.lucene.search. The scoring is very much dependent on the way documents are indexed. So it is important to understand indexing. Be sure to use the useful index searcher.explain query.doc to understand how the score for a certain matching document was computed. Generally, the query determines which documents match a binary decision, while similarity determines how to assign scores matching documents. Now we are considering integrating field values into a score in changing scoring in similarity. For instance, this query matches the same document as original query and computes the score matches the same this query matches the same document as original query and computes scores as similarity score plus 0.7 multiplied by feature score. While the class query in package.apache.lucene.search, the abstract class for queries here. While similarities helped score a document relatively to a query, it also common for a document hold features that measure the quality of a match. Such features are best integrated into the score by indexing feature field with the document at index time, and then combining the similarity score and the feature score using linear combination. For instance, this query matches the same document as original query. And compute the score similarity score plus 0.7 multiplied by feature score. The less efficient yet more flexible way of modifying scorers is to index scoring features into doc value fields and then combine them with the similarity score and then combine them with the similarity score using function score query. From the queries module. For instance, this example shows how to compute score as similarity score multiplied by with the similarity scoring using the function score query from the module queries module. For instance, this example shows how to compute scores as similarity score multiplied by method.log popularity using expressions module. And assuming that values for the popularity field have been set in now numeric doc values field at index time. compile an expression. Simple bindings just maps variables to score field, variables to short field instances. Create a query that matches based on the original query but scores using EXPR. Now we are considering custom queries expert level. The query class in custom queries expert level. The query class has several methods that are important for derived classes. The class query in package Lucene.search, the abstract class for queries. In some sense, the query class is where all it begins. Without a query, there would be nothing to score. Furthermore, the query class is the catalyst for other scoring classes, as it is often responsible for creating them or coordinating the functionality between them. The query class has several methods that are important for derived classes. One, create wait, index searcher, score mode, float boost. A wait is the internal representation of the query, so each query implementation must provide an implementation of wait. The rewrite index searcher method, the rewrite queries into primitive queries. Primitive queries are term query, boolean query, and other queries that implement create, wait, index searcher, score mode, float boost. Now we are considering search algorithm. Search algorithm. These important objects are involved in the search. The class index searcher in package Lucene.search implements search over a single index reader. This section is mostly notes. Now we are mostly notes on the stepping through a scoring process and served as fertilizer for the earlier sections. In the typical search application, queries pass to an index reader beginning the scoring process. One side of this, inside the index searcher is a collector is used for scoring and sorting of the search results. The important object involved in a search. One, the wait object of the query. The wait object is internal representation of the query that allows the query to be reused by index searcher to the index searcher that initiated the call. 3, the sort object for specifying how to sort the result if the standard score based method is not desired. Assuming we are not sorting, since sorting doesn't affect the raw Lucene score, we call one of the search method of the index searcher passing in the wait object created by index searcher.create wait query score mod float and the number of results we want. This method returns top-docs object which is an internal collection of the search results. Index searcher creates the top score doc collector and passes it along with the weight to another expert search method. For more on the collector mechanism, see index searcher. The top scorer doc collector uses priority queue to collect the top result for the search. At least we are actually going to score some documents. The score method takes in the collector, most likely the top score doc collector or top field collector, and does it business. Of course, here is where things get involved. Scorer that is returned by the weight object depends on what type of query has submitted. In the most real-world application with multiple query terms, the scorer is going to be Boolean scorer 2 created from the Boolean weight. Assuming Boolean scorer 2, we get an internal scorer based on the required optional prohibited part of the query. Using this internal scorer, the Boolean scorer 2, then proceed into the while loop based on doc iterator dot next doc method. The next doc method advances to the next document matching the query. This is an abstract method in the scorer class and is thus overridden by all derived implementation. If you have a simple or simple O query, your internal scorer is most likely a disjunction sum scorer, which essentially combines the scorers from the sub scorers of the odd terms. Now we are considering class expression. The example that shorts based on an expression. The Lucene 9.7.0 expression API. The expression module is the new to Lucene 4.6. It provides an API for dynamically computing per document values based on the string expressions. The class expression in package ogla.lucene.expressions, base class that computes the value of an expression for a document. Example that short based on an expression. Here the example that modify the scores produced by the query. Here the compile an expression. Here the simple bindings just maps variables to short field instances. Here the create short field and sort by it reverse order. Here the compile an expression. Simple binding just maps variables to the short field instances. Create a query that matches based on the body colon contents but it goes using exp expression here. Here we are considering Lucene 9.7.0 facet API, provides facet indexing and search capabilities. Now we are considering Lucene, the package, the package org.apache.lucene.search.grouping in Lucene 9.7.0 grouping API. A typical use for a generic two-pass search, grouping search look like this using the grouping convenience utility, optionally using caching for second pass search. The class group search in package org.apache.lucene.search.grouping convenience class to perform grouping in a non-distributed environment. A typical usage for a generic two-pass grouping search look like this, using grouping convenience utility, optionally using caching for second pass search. With regarding package org.apache.lucene.search grouping, the grouping there, this module enables search result grouping with Lucene, where it's the same value in the specified single value group field are grouped together. For example, if you group by an author field, then all documents with the same value of the author fall into the single group. Grouping requires a number of inputs. Group selector, this define how groups are created from values per document. Grouping module ships with selectors for grouping by term or by long and or double ranges. Group sort, how the groups are sorted. For you grouping sorting process, each group is represented by the highest sorted document according to the group sort within it. For example, if it's price ascending, then the group first group is the one of the lowest price booked within it. Or if you specify relevant group short, then the first group is the one containing highest scoring book. Top n groups, how many top groups to keep. For example, 10 means the top 10 groups are compiled. Group offset, which slice of top groups you want to retrieve. For example, 10 means the top 10 groups are computed. Group offset, which slice of the groups you want to retrieve. For example, 3 means you will get 7 groups back, assuming top n groups is 10. This is useful for paging, where you might show 5 groups per page. Within group sort, how the documents within each groups are sorted. This can be different from the group sort. Max docs per group. How many top documents within each group to keep. Within group offset, which slice of top documents you want to retrieve from each group. The implementation is to pass first pass grouping collector gathers top groups, and the second pass grouping collector gathers document within these groups. If the search is costly to run, may you want to use caching collector class. Which caches it hits and can quickly replay them for second pass. This way you only run the query once, but you pay a RAM cost to briefly hold all hits. Results are returned as top groups. This is within group sort. Groups are defined by group selector implementation. Term group selector groups based on the value of the sorted doc fields. Value source group selector groups based on the value of value source. Double range group selector groups based on the value of a double value source. Long range group selector groups based on the value of a long value source. The known limitation, sorting is not directly supported, though it is not too difficult if you can merge top groups and the top documents per group yourself. Typical usage for generic two-pass grouping search look like using grouping convenience utility, optionally caching for the second pass search. To use the single pass block grouping collector, first at indexing time you must ensure all the docs in the groups are added as a block. And you have some way to find last document of each group. One simple way to do is to add marker binary field. Then and then at the search time here, or alternatively use group search convenience utility. Another collector is all groups head collector that can be used to retrieve all most relevant documents per group. Set cache in MB. Require total group count. render grouped result. Create documents from your source. You can also use the writer.update document. Just be sure you replace then an entire previous doc block with this new one. For example, each group could have a group ID field with the same value for all docs in this group. Render group result. Now we are considering Lucene 9.7.0 highlight API. The package org.apache.lucene.search.highlight here, highlight in the API. This is an example usage. The class highlighter in package org.apache.lucene.search.highlight marks and highlighted terms found in the best sections of text using configurable fragmenter, scorer, formatter, encoder, tokenizers. The highlight package contains classes to provide keyword in context features typically used in highlight search terms in the text result pages. The highlighter class is a central component that can be used to extract most interesting sections of a piece of text and highlighting them with the help of fragmentator, fragment score, and formatter classes. Here is an example usage. Above create the documents with two fields, one with the term vectors TV and one without no TV. Term vector. Now we are considering package org.apache.lucene.monitor in Lucene 9.7.0 monitor API. A number of matches types are included. The class monitor in package org.apache.lucene.monitor. A monitor contains a set of query objects with associated IDs and efficiently matches them against set of document objects. A number of matches types included here. The and the in the package Lucene.monitor, the monitoring framework, this package contains classes to allow monitoring of a stream of document with a set of queries. Here the a number of matcher types are included. Query match.simple matcher just returns the set of query IDs that a document has matched. Scoring match with similarity org.apache.lucene.search.similarity.similarities returns a set of matching queries with the scores that each one records against document. Similar to scoring match but include full explanation, returns the matching queries along with the matching terms of each query. Matches can be wrapped in partition matcher or parallel matcher to increase performance in low currency systems. Now we are considering Lucene the Lucene 9.7.0 Spatial Extras API, the Spatial Extras module for Apache Lucene. The Spatial Extras module uses Spatial 4J heavily. Spatial 4J is an ASL license library with these capabilities here. The class Spatial strategy in package org.apache.lucene.spatial. The spatial strategy encapsulates an approach to indexing and searching based on shapes. The Spatial Extras module, new to Lucene for 6.5, is new home for original Lucene Spatial module. The principal interface is this module is spatial strategy, which can calculate approach to indexing and searching based on the shapes. Different strategies have different features and performance profiles, which are documented at each strategy implementation class level. For some sample code, the Spatial Extras module uses Spatial 4J heavily. The Spatial 4J is an ASL license library with these capabilities. Provides shape implementation, namely point, rectangle, and circle. Both geospatial context and plain 2D Euclidean Cartesian contexts are supported. With additional dependency, it adds polygon and other geometry shape supports via integration with JTS topology suite. This include dateline wrap support, shape parsing and serialization, including well-known text WKT via JTS, distance and other spatial related math calculations. Historical note, the Spatial Extras module was once known as Lucene Spatial Playground LSP as an external project. In March 2012, the LSP split into Spatial module as part of the Lucene and Spatial 4J externally. A large chunk of LSP implementation originated as SO LR2155, which uses tri-prefix tree algorithms with geohash encoding. That approach is implemented in recursive prefix tree strategy today. An example, we can consider class index searcher dot too many clauses thrown when an attempt is made to add more than get max clause count clauses. This typically happens if a prefix query, fuzzy query, wildcard query, or term range query is expanded to many terms during search. This is in package org.apache.lucene.search. As an error example, we can consider this error o.e.b. Elasticsearch uncaught exception handler. Fatal error occurred in thread existing and etc. And here at org.apache.lucene.search.search-index-search.searcher.search index-searcher.java 665 etc. This is occurred in the environment with Elastic stack and elastic search. Now we are focusing on search result. Here you can see a loop. You can also perform some searches in the search tab. Loop is the tool of choice to understand search results. It is a free Java utility that lets you analyze a Lucene index. You can perform some searches here in the search tab here. The search works using a series of one or more field name term predicates. For example, you can think of this one here, title : hello, here content type dot telnik. Note that the query is case sensitive. The field name should always use the exact same case here than the field name displayed, but the term should always be lowercase here. For adding a plus before predicate, here indicates it is mandatory. If you put plus here, searches for the content whose title contains both here content type and telnik. Here notice how the content type field indicates the type of the content you are dealing with here. When the result shows up when it shouldn't, it is generally because site infinity here is indexing a similar term of another type. The content type combined with the ID and sometimes the link field helps pinpoint the exact item being indexed. As an example, we can consider this one here. The class scoreDoc holds one hit in top docs. And here you can see this is assert equals 1 with the length, and iterate through the result here. And this is assert equal. This is the text to be indexed here. And here the score docs are in package org.apache.lucene.search. So here we are asserting the search result. As an error example, we can consider total hits cannot be converted to long. Now we are focusing on files to be indexed. A computer file is a computer resource for recording data in a compute storage device, primarily identified by its file name. Just as words can be written to a paper, so can data be written to a computer files. Files can be shared with and transferred between computers and mobile devices via removable media networks or the internet. Search engine indexing is the collecting, parsing, and storing of data to facilitate fast and accurate information retrieval. Index design incorporates interdisciplinary concepts from linguistics, cognitive psychology, mathematics, informatics, and computer science. An alternative name for the process in the context of search engine designed to find web pages on the internet is web indexing. Here we are considering adding a file to the index class file, an abstract representation of file and directory path names. This is in package java.io. Once we created the index directory, let's go ahead and add a file to the index. Here we create document with two string fields named path and file name, and a text field called contents. Note that we pass the file reader instance as the second parameter to the text field. The document is added to the index using index writer. The third argument in the text field or string field constructor indicate whether the value of the field will also be stored. Finally, we invoke the close method of the index writer to gracefully close and release the lock from the index files. Here we are considering index as a single document. Here interface path, an object that may be used to locate a file in a file system, will typically represent a system dependent file path. This is in package java.nio.file. This is here the make a new empty document. Here add the path of the file named path. Use a field that is indexed, that is searchable, but don't tokenize the field into separate words, and don't index term, frequency or positional information. Here at the last modified date of the file, a field name modified, use long point that is indexed, that is efficiently filterable with point range query. This indices to multi-second resolution, which is often too fine. You could instead create a number based on year, month, day, hour, minutes, seconds down the resolution you require. For example, long value 2011 021714 would mean February 17th 2011 2 to 3 p.m. Add the content of the file to the field name contents. Specify a reader so that the text of the file is tokenized and indexed but not stored. Note that the file reader expect the file to be UTF-8 encoding. If that's not the case, searching for special characters will fail. and the new index, so we just add the document. No, all document can be there, and adding file, and here this is the index writer. So if the existing index and all copy of this document may have been indexed, so we use update document instead to replace old one matching the exact path if it represent. Now we are focusing on Lucene analysis language analyzer. org.apache.lucene.analysis defines an abstract analyzer API for converting text from a reader into a token stream and enumeration of token attributes. A token stream can be composed by applying token filters to the output of the tokenizer. Tokenizers and token filters are strung together and applied with an analyzer. Analysis common provide a number of analyzer implementation, including stop analyzer and grammar-based standard analyzer. Here you can see analysis process during indexing. Fields 1 and 2 are analyzed, producing a sequence of tokens. Field 3 is unanalyzed, causing an entire value to be indexed as a single token. Here document has field 1, field 2, field 3, and field 1 is connected to analyze, field 2 is connected to analyze, analyze is connected to update index. Tokens are passed from analyze to update index, and field 3 is connected to update index, and update index is connected to indexed. Here you can see a token stream with the positional and offset information. A stream of tokens are fundamental output of analysis process. During indexing, fields designated for analysis are processed with the specified analyzer, and the important attributes from each token are then written to the index. For example, let's analyze the text the quick brown fox. Each token represents an individual word of that text. A token carries with it a text value, the word itself, as well as some metadata, start and end of the character, and character offsets in the original text, a token type, a positional increment. The token may optionally be contain application defined bit flags and arbitrary byte array payload, and can easily extend to include any application specific attribute. This figure shows details of a token stream analyzing this phrase with a simple analyzer. The start offset is the character position in the original text where the token text begins, and the end offset is the position just after the last character of the token text. These offsets are useful for highlighting matched token in search results. The token type is a string defaulting to word, that you can control and use the token filtering process if desired. As text is tokenized, the position relative to the previous token is recorded as the position increment value. Most of built-in tokenizers leave the position increment value at the default value of 1, indicating that all tokens are in successive positions, one after other. Each token has optional flags. A flag is a set of 32 bits stored in an int that's unused by Lucene's built-in analyzers but could be used by your application. Likewise, each token can have a byte array recorded in the index referred to as payload. Tokens into terms. After text is analyzed during indexing, each token is posted to the index as a term. The position increment start and end offsets and payloads are only additional metadata associated with the token that's recorded in the index. The token type and flags are discarded. They are only used during analysis process. Positional increments. The token position increment value relates to the current token's position to the previous token's position. Position increment is usually 1, indicating that each word is in a unique and successive position in the field. Position increments factor directly into performing praise queries and spam queries, which rely on knowing how far terms are from one another within the field. Position increments greater than 1 allow for gaps and can be used to indicate where words have been removed. A token with 0 position increment places the token in the same position as the previous token. Analyzers that inject synonyms can use a position increment 0 for synonyms. The effect is that praise queries work regardless of which synonym was used in the query. Here you can see the quick brown fox here, and you can see the offsets here, and positional increments are here. Here you can see a standard analysis pipeline. The Lucene analysis Java doc provides a good overview of the moving parts in the text analysis pipeline. At a high level, you can think of the analysis pipeline as consuming a raw stream of characters at the start and producing terms roughly corresponding to words at the end. The standard analysis pipeline can be visualized as such here. We will see how here you can see the input stream, standard tokenizer, lowercase filter, and stop word filter here. Here the Lucene is easy, Steve told us. Here the standard tokenizer, Lucene is easy, Steve. Here in this case, then input stream is connected to standard tokenizer. Standard tokenizer is connected to lowercase filter. Here Lucene is easy, Steve, lowercase L and S, and lowercase filter is connected to stop word filter. Here the Lucene easy, Steve told. Here you can see the workflow of the new token stream API as follows here. One instantiation of token stream, token filters which add or get attributes to or from the attribute source to consume the consumer called reset. 3. Consume retrieves attributes from the stream and store the local references to all attributes it wants to access. 4. The consumer calls increment token method until it returns false, consuming the attributes after each call. 5. The consumer calls end method so that any end of stream operations can be performed. 6. The consumer calls close method to release any resource when finished using the token stream. To make sure that the filters and consumers know which attributes are available, the attributes must be added during instantiation. Filters and consumers are not required to check for availability of attributes in increment token method. You can find some example code for new API in analysis package level Java doc. Sometimes it is desirable to capture the current state of a token, for example the buffering process. For this use case, a buffering process, the token stream API in Lucene is based on the decorator pattern. Therefore, all non-abstract subclasses must be final and have at least a final implementation of increment token method. This is checked when Java assertions are enabled. An example, we can consider this code segment. Here the class analyzer. An analyzer builds a token stream which analyzes text. It does represent the policy for extracting index terms from text. Here the standard analyzer filters standard tokenizer with standard filter, lowercase filter and stop filter using a list of English stop words. This class analyzer here is in package org.apache.lucene.analysis. As an example too, we can consider this code segment here. When you are invoking an analyzer, application usually do not invoke analysis. Lucene does it for them. Applications construct analyzers and pass them into Lucene as follows. At indexing as a consequences of add document doc, the analyzer in effect for indexing is invoked. For each index field is added to the document. At search, a query parser may invoke analyzer during parsing. Note that for some queries, analysis does not take place. For example, wildcard queries. However, an application might invoke analysis of any text for testing or for any other purpose, something like this. Here you can substitute desired Lucene version for X and Y here. Here standard analyzer or any other analyzer. The analyzer class will construct the tokenizer, token filters and char filters and pass the resulting readers to the tokenizer. Here reset this stream to the beginning required. Here they use attribute source dot reflect as string boolean for token stream debugging. Here perform end of stream operations, that is set the final offset, and finally release resources associated with this stream. An analyzer builds a token stream which analyzes text. It does represent a policy for extracting index terms from text. In order to define what analysis is done, subclasses must define their token stream components. In create components string, the components are then used in each call for token stream string reader. Here is a sample simple example. Here create a new analyzer token string components instance for this analyzer, and here in the normalize wrap the given token stream in order to apply normalization filters. Assuming foo filter is about normalization and bar filter is about stemming, only foo filter should be applied. So adding a length filter, here the class filtering token filter, abstract base class for token filters that may remove tokens. You have to implement a accept method and return a boolean if the current token should be preserved. Increment token method uses this method to decide if a token should be passed to the caller. This is in package org.apache.lucene.analysis. Here in the length filter, the char term attribute is added and stored in the instance variable. Remember that there can only be a single instance of char term attribute in the chain. So in this example, the add attribute call in the length filter returns the char term attribute that the white space tokenize already added. In the tokens are retrieved from the input stream in filtering tokens filters increment token method, which calls length filters accept method. That is not shown here. And by looking at the term text in the char term attributes, the length of the term can be determined. and tokens that are either too short or too long are skipped. Note how accept can efficiently access the instance variable, and no attribute lookups is necessary. The same is true for the consumer, which simply use local references to the attributes. As example 6, we can consider this one, hibernate.search.analyzer equal org.apache.lucene.analysis.es.spanish analyzer. This is configuring an analyzer in OpenKM. For that, edit the $tomcat_home /openkm.configure cfj file and add this line here. And now here as an example, we are considering package org.apache.lucene.analysis text analysis API and code to convert text into indexable or searchable tokens, covers, analyze, and reader classes. Now we are considering parsing, tokenization, analysis in package org.apache.lucene.analysis. Lucene and indexing and search library accept only plain text input. Now we are considering parsing. Applications that build their search capabilities upon Lucene may support documents in various formats: HTML, XML, PDF, Word, just to name a few. Lucene does not care about the parsing of these and other document formats, and it is the responsibility of the application using Lucene to use the appropriate parser to convert the original format into the plain text before passing that plain text to Lucene. Now we are considering tokenization. There are many post-tokenization steps that can be done, including but not limited to plain text passed to the to Lucene for indexing goes through a process generally called tokenization. Tokenization is the process of breaking input text into small indexing element tokens. The way input text is broken into tokens heavily influences how people will then be able to search for that text. For instance, sentences beginning and ending can be identified to provide more accurate trace and proximity searches, though sentence identification is not provided by Lucene. In some cases, simply breaking the input text into tokens is not enough. A deep analysis may be needed. Lucene includes both pre- and post-tokenization analysis facilities. Pre-tokenization analysis can include, but it is not limited to, stripping HTML markup and transforming or removing text, matching arbitrary patterns or sets of fixed strings. There are many post-tokenization steps that can be done, including but not limited to stemming, replacing words with their stems. For instance, if the English stemming bikes is replaced with bike, now query bike can find both documents containing bike and those containing bikes. Stop words filtering. Common words like the and rarely add any value to a search. Removing them shrinks the index size and increases performance. It may also reduce some noise and actually improve search quality. Text normalization. Stripping accent and other character makings can make for better searching. Synonym expansion. Adding a synonym at the same token position as the current word can mean better matching when users search with words in the synonym set. Now we are considering co-analysis. These are here. The class analyzer in package org.apache.lucene.analysis. An analyzer build token streams which analyze text, thus represent a policy for extracting index terms from text. Class char filter in package org.apache.lucene.analysis. Subclasses of char filter can be chained to filter a reader. They can be used as a reader with additional offset correction. Tokenizers will automatically use correct offset int if the char filter subclass is used. Class tokenizer in package queryParser Lucene.analysis. A tokenizer is a token stream whose input is a reader. Class token filter in package queryParser Lucene.analysis. A token filter is a token stream whose input is another token stream. The analysis package provides a mechanism to convert strings and readers into tokens that can be indexed by Lucene. There are 4 main classes in the package from which all analysis processes are derived. These are analyzer. An analyzer is responsible for supplying a token stream which can be consumed by indexing and searching processes. Most of the time you can use an anonymous subclass of analyzer. Char filter extends reader to transform the text before it is tokenized while providing corrected character offsets to account for those modifications. This capability allows highlighting to function over the original text when indexed tokens are created from the char filter modified text with offset that are not same as those in the original text. Tokenizer.setReader java.io.reader accept char filters. Char filters may be chained to perform multiple pre-tokenization modifiers. Tokenizer. A tokenizer is a token stream and is responsible for breaking up incoming text into tokens. In many cases, an analyzer will use a tokenizer as the first step in the analysis process. However, to modify text prior to tokenization, use a char filter subclass. Token filter is a token stream and is responsible for modifying tokens that have been created by the tokenizer. Common modification performed by the token filter are deleting, stemming, synonym injection, and case folding. Not all analyzers require token filters. Now we are considering hints, tips and traps. To ease this confusion, here is some clarifications. The relationships between analyzer and char filters and tokenizers and token filters is sometimes confusing. To ease this confusion, here are some clarifications. The analyzer is a factory for analysis chains. Analyzers don't process text. Analyzers construct char filters, tokenizers, or token filters that process text. An analyzer has 2 tasks: to produce token streams that accept a reader and produces tokens, and to wrap or otherwise pre-process reader objects. Char filter is a subclass of reader that supports offset tracking. The tokenizer is only responsible for breaking the input text into tokens. The token filter modifies the stream of tokens and their contents. Tokenizer is a token stream, but analyzer is not. The analyzer is field aware, but tokenizer is not. Analyzers may take field name into account and when constructing a token stream. If you want to use particular combination of char filters, a tokenizer and some token filters, the simplest thing is open and create an anonymous subclass of analyzer. Provide analyzer.create component string and perhaps also analyzer.initReader string java.io.reader. However, if you need some same set of component over and over in many places, you can make subclasses of analyzer. In fact, Apache Lucene supplies a large family of analyzers class that deliver useful analysis chains. Most common of these is the standard analyzer. Many applications will have a long and industrious life with nothing more than standard analyzer. The analyze common library provides many pre-existing analyzers for various languages. Analysis command library also allows to configure custom analyzer without subclassing using the custom analyzer class. Aside from the standard analyzer, Lucene includes several components containing analysis components, all under the analysis directory of the distribution. Some of these support particular languages, other integrate external components. The common subdirectory has some noteworthy general purpose analyzers, including per field analyzer wrapper. The most analyzers perform some same operation on all fields. The per field analyzer wrapper can be used to associate a different analyzer with different fields. There's a great deal of functionality in the analysis area. You should study it carefully to find the pieces you need. Analysis is one of the main causes of slow indexing. Simply put, the more you analyze, the slower the indexing in most cases. Perhaps your application would be just fine using simple white space tokenizer combined with a stop filter. The benchmark library can be useful for testing out the speed of the analysis process. Now we are considering invoking an analyzer. However, an application might invoke analysis of any text for testing or any other purpose. Application usually do not invoke analysis. Lucene does it for them. Applications construct analyzers and pass them into Lucene as follows. At indexing, the consequence of at document.doc method, the analyzer effect for indexing is invoked for each index field of the added document. At search, the queryParser may invoke analyzer during parsing. Note that for some queries, analysis does not take place. For example, wildcard queries. However, an application might invoke analysis of any text for testing or for any other purpose, something like here. Here the class analyzer in package org.apache.analysis, apache.lucene.analysis, an analyzer built token streams which analyze text. It does present a policy for extracting index term from text. Substitute desired Lucene version for XY or any other analyzer here. Analyzer class will construct the tokenizer token filters and char filters and pass the resulting reader to the tokenizer. Reset this stream to the beginning required. Use attribute source dot reflex as string boolean for token stream debugging. Perform end of the stream operations, for example, set the final offset. Release the resources associated with these streams. Now we are considering indexing analysis versus search analysis. Here are some rules of thumb. Selecting the correct analyzer is crucial for search quality and can also affect indexing and search performance. The correct analyzer for your application will depend on what your input look like and what problems you are trying to solve. Lucene's Java wiki page analysis paralysis provides some data on analyzing your analyzer. Here are some rules of thumb. One, test. Did we say test? 2, beware of too much analysis. It must hurt indexing performance. 3, start with same analyzer for indexing and search. Otherwise, searchers would not find what they are supposed to. 4, in some cases, different analyzer is required for indexing and search. For instance, certain searches require more stop words to be filtered. For example, filters that is more than those that were filtered at indexing. Query expansion by synonyms, acronyms, auto spell correction, etc. This might sometimes require a modified analyzer. Now we are considering field section boundaries in implementing your own analyzer and analysis components. Where decides this behavior can be modified by introducing position in a position gap between consecutive field sections simply by overriding analyzer.getPosition increment gap field name. When document.add field is called and the class standard analyzer in package apache.lucene.analysis.standard filters standard tokenizer with lower case filter and stop filter using configurable list of stop words. Field section boundaries when document.add field is called the multiple times for the same field name, we could say that each such call creates a new section for that field in the document. In fact, a separate call to token stream field reader would take place for each of these so-called sections. However, the default analyzer behavior is to treat all these sections as one large section. This allows price search and proximity search to seamlessly across boundaries between sections. In other words, if a certain field F is added like this, then the price search for end starts would find that document. When desired, this behavior can be modified by introducing a position gap between consecutive field sections simply by overriding analyzer dot get position increment gap field name. The substitute desired Lucene version for XY. Now we are considering white space tokenization in example in token stream API. In this example, we will create a white space tokenizer. and use a length filter. In this easy example, a simple white space tokenization is performed. The main loop loop consumes white space tokenization is in main method loop consumes a stream and prints the term text of the tokens by accessing the char term attributes that the white space tokenizer provides. Here is the output. Text to tokenize. Substitute the desired Lucene version for XY. Get the char term attributes from the token stream. Print all tokens until stream is executed. Stream is exhausted. Now we are considering a class token stream. This is an abstract class. Concrete subclasses are here. The class token stream in package .apache.lucene.analysis. A token stream enumerates the sequence of tokens either from fields of a document or from query text. A token. This is an abstract class. Concrete subclasses are tokenizer, a token stream whose input is a reader, and token filter, a token stream whose input is another token stream. Token stream extends attribute source, which provides access to all of the token attributes for the token stream. Note that one instance per attribute IMPL is created and reused for every token. This approach reduces the object creation and allows local caching of references of the attribute IMPLs. Now we are considering Lucene 9.7.0 Common API and the analysis for Lucene content in different languages and domains. Here the class English analyzer in package org.apache.lucene.analysis.en analyzer for English. Now we are considering Lucene 9.7.0 ICU API. This module exposes functionality from ICU to Apache Lucene. ICU4J is a Java library that enhances Java internationalization supported by improving performance, keeping current with Unicode standard and providing richer APIs. Here you can see the tokenizing multi-language text in as example usage. Here the class ICU tokenizer in package Apache.lucene.analysis.icu.segmentation. Class the breaks text into words according to UAX #29 Unicode text segmentation. This will work well in general for most languages. Now we are considering Lucene 9.7.0 Kuromochi API. Kuromochi is an morphological analyzer for Japanese text. The class Japanese analyzer in package Apache.lucene.analysis.ja analyzer for Japanese that uses morphological analysis. Now we are considering Lucene 9.7.0 morphologic API. This package provides dictionary-driven lemmatization, accurate stemming, filter, and analyzer for Polish language driven by the morphologic library developed by David Weiss and Martin Milswoki. The class morphologic analyzer in package Apache.lucene.analysis.morphologic analyzer using morphologic library. The Lucene 9.7.0 Nori API. Nori is a morphological analyzer for Korean text. Class Korean analyzer in package org.apache.lucene.analysis.ko analyzer for Korean that uses morphological analysis. Lucene 9. Now we are considering Lucene 9.7.0 Open NLP API. This module exposes functionality from Apache Open NLP to Apache Lucene. The Apache Open NLP library is a machine learning based toolkit for processing of natural language text. Open NLP tokenizer, the class Open NLP tokenizer in package Apache.lucene.analysis.openLP run OpenNLP sentence detector and tokenizer. The index of each sentence is stored in sentence attribute. Now we are considering Lucene 9.7.0 phonetic API. Analysis for indexing phonetic signatures for sound alike search. Class phonetic filter in package org.apache.lucene.analysis.phonetic. Create tokens for phonetic matches. Now we are considering Lucene 9.7.0 Smart CN API. Analyze for simplified Chinese which indexes words. The class Smart Chinese Analyzer in package org.apache.lucene.analysis.cn.smart. Smart Chinese Analyzer is an analyzer for Chinese, so mixed Chinese-English text. The analyzer uses probabilistic knowledge to find the optimal word segmentation for simplified Chinese text. The text is first broken into sentences, then each sentence is segmented into words. Now we are considering Lucene 9.7.0 Stempel API. Stempel the algorithmic stemmer for Polish language. The class Stempel stemmer in package org.apache.lucene.analysis.stempel. Stemmer class is a convenient facade for other stemmer related classes. The core stemming algorithm and its implementation is taken verbatim from the Egoto project, www.egoto.org. An exception example, we can consider this one, IO exception. This can be occurred in method public standard analyze. This can be occurred in constructor public standard analyzer reader stop words. in the class standard analyzer. As an error example, we can consider this one package org.apache.lucene.analysis does not exist. Import org.apache.lucene.analysis.analyzer. Now we are focusing on index core. Index core is the direct focus when manipulating file indexes. Now we are focusing on Lucene index. Indexer org.apache.lucene.index provides two primary classes: index writer, which creates and adds documents to indices, and index reader, which accesses the data in the index. Here you can see two main processing flow: index update and index search. Document indexing, here the given a document, add it into the index, and document retrieval for a given query, retrieve the most relevant document from the index. Here you can see raw data and parser in index update. Doc is connected to fields, and fields are connected to terms, and you can see the analyzer here, lowercase remove stop words stemming, and index writer is connected to inverted index, and you can see the directory here, and index reader is connected to the inverted index. Here you can see statistics, delete, undelete docs, and inverted index is connected to the index searcher. Here you can see, and you can see the hits also, and filtered by Boolean model, is scored by a vector space model cosine. It says model cosine distance of query and doc, and controlled by boosting. Here query language, and here you can see the query parser. You can see the term query. You can see the query here: term query, trace query, Boolean query, range query. Query is connected to the fields, and fields are connected to the term. You can see analyzer here, and you can see the index searcher here. Here you can see Lucene indexing mechanism. Here to index data with Lucene, first of all we must convert it to a stream of plain text tokens. Therefore, other patterns of files must be converted into text before being indexed. Secondly, create a document object with its relevant field object, then call the method addDocument. To store the data for indexing. Next, use the specified analyzer to tokenize every word of indexes so that the data stream can be more suitable to be indexed. Last but not least, write the result back to the index files. The process of building full text indices is presented in this figure. Here you can see files to be indexed. Here .html, .text, .doc, .pdf. These are connected to document processing. Here you can see file patterns to be converted and add document. Document processing is connected to language analyzer. Language analyzer is connected to index files. Here you can see Lucene based full text search contains index management and search index. Its data handling process is like this figure. Here bean index document is connected to exceedance analyzing logic. Text stream is passed from bean index document to exceedance analyzing logic. Query sentences are connected to exceedance analyzing logic. Text stream is passed from query sentences to exceedance analyzing logic. Exceedance analyzing logic is connected to construct index logic. Meta word stream is passed from exceedance analyzing logic to construct index logic. Exceedance analysis logic is connected to query sentences exceedance analysis logic. Meta word stem is passed from exceedance analyzing logic to query sentences exceedance analyzing logic. And query sentences exceedance analyzing logic is connected to index query logic. Query sentences object stream is passed from query sentences exceedance analysis logic to index document query logic. Construct index logic is connected to storage abstract. Byte stream is passed from construct index logic to storage abstract. Index document is connected to storage abstract. Byte stream is passed from index document to storage abstract. Storage abstract is connected to index query index document query logic. Storage byte stream is passed from index storage abstracts to index document query logic. Index document query logic is connected to estimate and composer. Meta word stem is passed from index document query logic to estimate and composer logic. Estimate and composer logic is connected to query result. Text stream is passed from estimate and composer logic to query results. Here you can see inverted index implementation. First we can discuss about index structure. Both document and query is represented as a bag of words. In Apache Lucene, document is the basic unit for storage and retrieval. A document contains multiple fields, also called zones. Each field contains multiple terms equivalent to words. To control how the document will be indexed across its containing fields, a field can be declared in multiple ways to specify whether it should be analyzed pre-processing step during index participate in the index, or stored in the case it need to be returned in the query result. Keyword not analyzed, indexed, stored. Unindexed, not analyzed, not indexed, stored. Unsorted, analyzed, indexed, not sorted. Text analyzed, indexed, sorted. Stored. In unstored, analyzed, indexed, and not stored. Inverted index is a core structure of the storage. It is organized as an inverted manner from terms to the list of documents which contains the terms. The list known as posting list is ordered by the global ordering, typically by document ID. To enable faster retrieval, the list is not just a single list but a hierarchy of skip list. This data structure is illustration here based on Lucene's implementation. It is stored on disk as segmented files, which will be both to memory during processing. Here the fields are connected to terms. Terms are connected to document frequencies, and terms are connected to documents. A term is connected to document, and document is connected to positions here list, and it has a term frequency, and document is connected to another document like that, likewise here. And in index segment Lucene implementation, field definitions are here, field whether index and stored and offset, and this record is connected to, this line is connected to field here, posting list, field term doc frequency, offset here 2, and it's connected to frequency here as a doc frequency, and offset here here it is 3, and this is connected to position here 1920 here. Here you can see the additional forward index. The whole index contain an additional forward index as here. Here the document is connected to fields, and fields connected to terms, and term you can see the term frequency here, and terms is connected to positions, and here you can see other documents. Here you can see indexing diagram. In Lucene index algorithm, two basic algorithms, one make an index for a single document, and two match a set of indices. Incremental algorithm maintain stack of segmented indices, create index for each incoming document, push new indices into the stack, and then merge. Optimization, single doc indices kept in RAM, saves system calls. Here b equal 3 and 11 documents indexed. Stack has 4 indices. Gray indices have been deleted. Five mergers have occurred here. You can see the document indexing here. In document indexing, the document in its raw form is extracted from a data adapter. This can be making an web API to retrieve some text output, or crawl a web page, or receiving an HTTP document upload. This can be done in a batch or online manner. When the index processing is start, it presses each raw document and analyze its content. Typical steps include tokenize the document, break down into words, lowercase each word to make it non-case sensitive, but need to be careful with names and abbreviations. Remove stop words, take out high frequency words like the, but need the careful with phrases. Stemming, normalize different form of same word. For example, reduce run, running, ran into run. Synonym handling, this can be done in two ways. Either expand the term to include synonyms, its synonyms, that is, if the term is huge, add gigantic and big, or reduce the term to a normalized synonym, that is, if the term is gigantic or huge, changing it to big. At this point, the document is composed with multiple terms. Document equals term 1, term 2, etc. Optionally, the terms can be further combined into n-grams. After that, we count the term frequency with this document. For example, in a bigram expansion, the document will become document 1 doc1 implies term 1 colon 5, term 2 colon 8, term 3 colon 4, term 1 underscore 2 colon 3, term 2 underscore 3 colon 1. We may compute a static score based on some measure of the quality of the document. After that, we insert the document into posting list. If it exists, otherwise create a new posting list for each terms of n grams. This will create an inverted list structure. There is a boost factor that can be set to the document or field. The boosting factor effectively multiply the term frequency, which effectively affecting the importance of the document or field. Document can be added to the index in one of the following ways: inserted, modified, and deleted. Typically, the document will first added to the memory buffer, which is organized as an inverted index in RAM. When this is a document insertion, it goes through the normal indexing process to analyze the document and build an inverted index list in RAM. When this is a document deletion, the client request only contains the doc ID. It reflects the forward index to extract the document content, then goes through the normal indexing process to analyze the document, build an inverted list. But in this case, the doc object in the inverted list labeled as deleted. When this is a document update, the client request contain the modified document. It is handled as a deletion followed by an insertion, which means the system first fetch the old document from the forward index to build an inverted list with nodes marked deleted, and then build the new inverted list from the modified document. For example, if doc1 equal AB is update to AC, then the posting list will be A colon doc1 deleted implies doc1, B colon doc1 deleted, C colon doc1. After collapsing A, the posting list will be A colon doc1, B colon doc1 deleted, C colon doc1. As more and more documents are inserted into the memory buffer, it will become full and will be flushed to a segment file on the disk. In the background, when M segments have been accumulated, Lucene merges them into bigger segment files. Notice that the size of the segment files at each level is exponentially increased. M to the power 2, M to the power 3. This maintains the number of segment files that need to be searched per query to be at the big O log n complexity, where n is the number of documents in the index. Lucene also provides explicit optimize call that merges all segment files into one. Here let's details a bit on the merging process. Since the posting list is already vertically ordered by terms, and horizontally ordered by doc ID, merging two segment files S1 and S2 is basically as follows. Walk through the list of both S1 and S2 together in the walk the posting list from the both S1 and S2 together in shorter term order. for those non-common terms that appeared in one of S1 or S2 but not both, write out the posting list to a new segment S3. Until we find a common term T, we merge the corresponding posting list from these two segments. Since both lists are sorted by doc ID, we just walk through both posting lists to write out the doc object to a new posting list. When both posting lists have same doc, which is the case when the document is updated or deleted, we pick the latest doc based on the time order. Finally, doc frequency of each posting list of the corresponding term will be computed. Here you can see merge factor equal m and can explicitly call index writer dot optimize to merge all segment into one single document. Here you can see doc1, doc2, doc3 is connected to memory buffer posting list. After m documents are added, write out the posting list to the index segment here, level 1, and clear the memory buffer. Here the memory buffer is connected to index segment, here level 1, and index segments of level 1 are connected to index segments of level 2. If there is already m segments at level 1, step 1, merge m segments level 1 to a new segment of level 2 and clear the m segments of level 1. And here you can see hold the index of m documents here and hold the index of m to the power 2 documents here, and index segments of level 2 are connected to index segments of level 3 here, and here holds the index of m to the power 3 documents here. Here in for large, here you can see document partitioning. For large corpus like web documents, the index is typically distributed across multiple machines. There are two models of distribution: term partitioning and document partitioning. In document partitioning, documents are randomly spread across different partitions where the index is built. In term partitioning, the terms are spread across different partitions. We will discuss the document partitioning as it's the most commonly used. Distributed index provided by other technologies that is built on Lucene, such as Elasticsearch. A typical setting is as follows. In this setting, machines are organized as columns and rows. Each column represents a partition of documents, while each row represents a replica of whole corpus. During document indexing, first row of the machine is randomly selected and will be allocated for building the index. When the new document is crawled, a column machine from the selected row is randomly picked to host the document. The document will be sent to this machine where the index is being built. Updated index will be later propagated to other rows of replicas. During document retrieval, the first row of the replica machine is selected. The client query will then broadcast to the every column machine of the selected row. Each machine will perform the search on its local index and return the top M elements to the query processor, which will consolidate the result before sending back to the client. Notice that k divided p less than m less than k, where k is the top k documents the client expects and p is the number of columns of the machine. Notice that m is the parameter that needed to be turned. One caveat of this distributed index is that as the posting list is split horizontally across partitions, we lost the global view of IDF value, without which the machine is unable to calculate TF-IDF score. There are two ways to mitigate that. Do nothing. Here we assume the document is evenly spread across different partitions to the local IDF represent a good ratio of the actual IDF. 2 extra round trip. In the first round, query is broadcast to every column of the return to its local IDF. The query processor will collected the IDF response and compute the sum of the IDF. In the second round, it's broadcast the query along with the IDF sum to each column of the machine, which will compute the local score based on the sum. Here you can see term partitioning, machine T1, term 1, term 2, machine T2, term 3, term 4, term 5. And here you can see machine D1, doc 1, doc 2. Here machine D2, this is document partitioning. Machine D2, doc 3, doc 4, doc 5. Here machine D3, doc 6, doc 7. This is about distributed index here. And here you can see a client query and pick a random row and scatter together, and this is connected to partition 1 replica, partition 2 replica, partition 3 replica. Here you can see the row 1 and row 2. Here you can see the crawler randomly pick 1, and here you can see the indices, and here you can see the inverted index. Here this inverted index connected to this one, and here this inverted index is connected to this one of the row 1, and this here the partition 3, the inverted index is connected to this one. Here you can see the structure of Lucene index. The Lucene index is stored in a single directory in the file system on a hard disk. The core element of the Lucene index are segments, documents, fields, and terms. In Lucene index, every index consists of one or more segments. Each segment contains one or more documents. Each document has one or more fields, and each field contains one or more terms. Each term is a pair of string representing a field name and a value. So a segment consists of series of files. Pictorially, the entire structure of a Lucene index can be represented as shown in this figure here. Exact number of files that constitute each segment varies from index to index and depends on the number of fields that the index contains. All files belonging to the same segment share a common prefix and differ in the suffix. One can think of segment as a subindex, although each segment is not fully independent index. Here you can see the index here. Segments is inside index, and document or documents are inside segments, and here the in segment, and fields are in documents, and terms are in fields, and pair of strings are in term. Field name and field value are in pair of strings. Now we are considering Lucene index. A Lucene index is an inverted index. An inverted index means that the content of the documents that are analyzed has their important terms indexed as a pair consisting of a field name and a field value. A field contains many terms that point to the corresponding document. To summarize, an inverted index makes the process of retrieving documents from a system breeze. Finally, the documents are searched in the fields and their values. A Lucene index consists of many segments. A segment is created every time when new document is created and indexed. Hence, each segment has many documents stored in it. The document consists of index fields. An index field is a pair consisting of a field name and field value pairs. Fields are used for calculating weights and ranking each search result. Here you can see the index is connected to segments. Segments is connected to documents, and document is connected to here fields. Here you can see the Lucene indexing architecture. The entire indexing procedure can be summarized as shown in this figure. Here the source data is connected to source specific parser, and it is connected to PDF parser, HTML parser, XML parser, user defined parser. Source specific parser is connected to analyzer, and it is connected to white space, simple, standard, etc. And analyzer is connected to index. Here you can see the basic internal structure of an index. This figure shows the basic internal structure of an index. The data in a segment is represented abstractly rather than as a realistic representation of actual data structure. Index. This is similar conceptually to database table, but differ in some important ways. The table in traditional relational database or NoSQL database needs to at least have its scheme defined when it is created. There are some clear constraints on the definition of the primary key, columns, and the like. However, there are no such constraint in Lucene index. Lucene index can be understood as a document folder. You can put a new document into the folder, or you can take one out, but if you want to modify one of the document, you must first take it out, modify it, and then put it back in the folder. You can put all sort of document in the folder, and Lucene can index the document whatever the content. Document, similar to a row in a relational database, so a document in a document database. An index can contain multiple documents. A document written into an index is assigned a unique ID. That is the sequence number, more usually called doc ID. Sequence numbers are doc ID. Field. One document is made up of one or more fields. A field is the smallest definable unit in data index in Lucene. Lucene provides many different types of field, including string field, text field, and numeric data values field. Lucene determines the type of indexing, such as inverted index, stored field, doc values, or n-dimensional, to use for the data depending on the field type, the type of the field type. Field and field type field type. The term and term dictionary, smallest unit of index and the search in Lucene. Field consists of one or more terms. The term is produced when a field is put through an analyzer, tokenizer. The term dictionary is the basic index used to perform conditional searches on terms. Segment. An index is composed of one or more sub-indexes. A sub-index is called segment. The conceptual design of segment in Lucene is similar to LSM, but there are some differences. They inherit the data writing advantage of LSM, but only provide near real-time but not real-time queries. When Lucene writes the data in first write to a in-memory buffer similar to memtable in LSM but not readable. When the data in the buffer reaches a certain amount, it will be flushed to become a segment. Every segment has its own independent index and are independently searchable, but the data can never be changed. This scheme prevents from random writes. Data is written as batch or as an append or achieves a high throughput. The documents written in segment cannot be modified, but they can be deleted. The deletion method does not change the file in its original internal location, but the doc ID of the document to be deleted is saved by the another file to ensure that the data file cannot be modified. Index queries need to query multiple segments and merge the result, as well as handling deleted document. In order to optimize queries, Lucene has a policy to merge multiple segments, and in this regard is similar to LSM's merge of SS table. Before segments are flushed or committed, data is stored in a memory and is unsearchable. There is another reason why Lucene is said to provide near real-time and not real-time queries. After reading the code, the reason for this is the searching of data in Lucene relies on the index setup. For example, the inverted index relies on term dictionary, and the data index in Lucene is set up during segment flush and not in the real time. The purpose of this is to set up the most efficient index. Naturally, it can introduce another index mechanism that set up the index in real time as it is written, but implementation of such mechanism would differ from the current index in the segment, needing the introduction of extra index at the right time and an extra query mechanism involving some degree of complexity. Sequence number. A sequence number is called doc ID. Doc ID is an important concept of Lucene. The database uniquely identifies a row using primary key, while Lucene index uniquely identifies the doc by its doc ID. However, the following points should be kept in mind. One, the doc ID is not actually unique to index, but is unique to a segment. Lucene does this mainly to optimize the writing and compression. Since it is only unique to a segment, how can a doc be uniquely identified at the index level? The solution is simple. The segments are ordered. To take simple example, an index has two segments, and each segment has 100 docs. Respectively, the doc IDs in segment are 0 to 100, but when they are converted to the index level, the range of doc IDs in the second segment is converted to 100 to 200. Doc ID is unique within a segment, numbered progressively from 0, but this does not mean the doc IDs are continuous. When a doc is deleted, there is a gap. 3. The doc ID corresponding to a document can change, usually when segments are merged. The inverted index, a very core of Lucene, is essentially list mapping each term to the doc IDs of the document containing the term. So when Lucene is searching internally, it makes a two-phase query. First phase is to list the doc IDs found to contain the given term. So when the Lucene is searched, and the second phase is to find the doc based on the doc ID. Lucene provides functionality to search by term as well as to query on the basis of doc ID. Doc ID is basically an int32 value starting from 0, which is an important optimization. Also reflected in the compression and query efficiently. This includes such optimization as a delta policy for data compression, zigzag code, skip list used in inverted index list. These are here you can see doc in-memory buffer segments, and segments are in index. Doc is connected to in-memory buffer via add document, and in-memory buffer is connected to segments via flush. Here the as an example, here segment 0, 1 and 2 is connected to segment 4 via merge. Here the in a segment you can see doc IDs and doc, and here the as an example here the doc ID 4, the doc 4 is connected to here doc 4 here. It has fields and values. Here you can see the basic relationships between different types of fields and fields in Lucene. Lucene supports many types of field, and each type of field determines the supported data type and index modes. Currently, the supported field types include long point, text field, string field, and numeric doc values field. This figure shows the basic relationship between different types of field in Lucene. All field types inherited from the class field. The field has three main attributes: name, string, and field data, bytes ref, and type, field type. Attribute name is the name of the field. Field's data is the name of the value. The value of all types fields are ultimately represented as binary byte streams. The attribute type is the type of field which determines how field is indexed. Field type is an important class containing many important attributes. The value of these attributes decide how the field is indexed. Lucene provides many many types of fields. There are two essential differences. First difference is the different types of values in the field define different conversion methods, and the second is the defining combination of different values in different attributes of field types. In this mode, you can customize customize types using custom data and combining the index parameters in the field type. You only have to understand the specific meaning of each attributes in the field type to know what index modes Lucene can provide. Let's look at them one by one. Stored indicates whether to save the field. If false, Lucene does not store the value of the field, and document returned in the query result will only contain saved field. Tokenized represent whether or not to tokenize. In Lucene, only a text field needs to be tokenized. Term vector. Here we explain the concept of term vector. That simply put, the term vector saves all information related to term, include term value, frequencies, positions. It is per document inverted index and provide functionality to find all term information in the document according to doc ID. It is not recommended to enable term vector for short fields because all the term information can be obtained by tokenizing once again. However, it is recommended to enable term vector for longer fields, so fields with the high cost tokenization. There are two main uses of term vector. First is keyword highlighting, and the other one is similarity matching between documents, more like this. Omit norms. Norm stands for normalization. Lucene enables every field in every document to have normalization factor saved. This is a coefficient related to scoring during searches. It only takes 1 byte to save the norms, but separate norm is saved in every field of every document, and every piece of norms data is loading into memory. So enabling norms consumes additional storage space and memory, but if you disable norms, you cannot use index time boosting. Elasticsearch officially recommends using query time boosting instead than length normalization. Index options. Lucene provides 5 optional parameters for inverted index: none, docs, doc and freaks, docs and freaks and positions, and doc and freaks and positions and offsets, which are used to select whether the field needs to be indexed and what content to index. Doc values type. Doc value is an forwarded index introduced in Lucene 4.0 doc ID to field column store, greatly enhancing the efficiency of sorting, faceting, and aggregation. Doc values is a storage structure with a strong schema, so all fields with doc values enabled must have exactly the same type. Currently, Lucene only provides 5 types of numeric binary: sorted numeric, and sorted set. Dimension. Lucene supports indexing of multidimensional data, employing special indexing to optimize querying of multidimensional data. Most typical usage scenario of this type of data is the index geographical location. This is an indexing method generally used for latitude, longitude data. Here you can see the subtypes, fields, long point, subtype field, long point, string field, text field, numeric, doc, value field, and here you can see the string name, byte ref, field data, field type. See the field types: stored, tokenized, term vector. Here with under term, store term vector, store term vector, offset, store term vector, position, store term vector, payload. And omit norms, index options, doc value types, and dimensions. Dimension count, dimension num bytes. Here you can see the structure of Lucene segment. Here the Lucene 4.0 we are considering. Lucene uses a well-known inverted index representation with additional functionality of keeping adjacent non-inverted data on a per-document basis. Both in-flight and persistent data uses variety of encoding schema that affect the size of the index's data and the cost of data compression. Lucene uses pluggable mechanism for data coding and for actual storage of index data. Directory API. Incremental updates are supported and stored in indexed extent, refers to as segments that periodically merge into larger segment to minimize the total number of index parts. The document model document model, the documents are modeled in Lucene as a flat ordered list of fields with the content. Fields have name and content data, float weight used for scoring, and loose letter for scoring, and the other attributes depending on the type, which together determine how the content is processed and represented in the index. There can be multiple fields in the same name in the documents. In which they can or will be processed sequentially. Documents are not required to have a unique identifier, though they often carry a field with this role for application level unique key lookup. In the process of indexing, document are assigned internal integer identifiers. Field types. There are two broad categories of fields in Lucene document. Those carry content to be inverted, indexed field. And those which content of the to be stored as is the stored field. Fields may belong to either or both categories. For example, with content both to be stored and inverted. Both index and stored fields can be submitted for storing and or indexing, but only stored fields can be retrieved. The inverted index can be accessed as and traverse being using a specialized API. Index fields can be provided in plain text, in which the case it will first pass through a text analysis pipeline, and it is or in its final form of a sequence for tokens of tokens with attributes, so-called token stream. Token streams are then inverted and added to the in-memory segments, which are periodically flushed and merged depending on the field options. Various token attributes such as positions, starting or coding offset or position payloads are also stored in the inverted data. It is possible, for example, to omit positional information while still storing the in-document terms frequencies. On per field basis, a variant of an index field is a field where the creation and storage of term frequency vectors are requested. In this case, the token stream is used also for building a small inverted index consisting of data from current field only, and this inverted data is then stored on the per document or per field basis. Term frequency vectors are particularly useful when they're performing document highlighting or relevance feedback, or when generating search result snippet region of the text that best matches the query terms. Stored fields are typically used for storing auxiliary per document data that is not searchable but would be cumbersome to obtain otherwise. For example, it would require retrieval from a separate system. This data is stored as byte arrays but can be manipulated through a more convenient API that present it as a UTF-8 strings, numbers, arrays, etc. Or optionally, it can be stored using strongly typed API, so-called doc values, that can use more optimized storage format. This kind of strongly typed storage is used for example to store per document, per field weight, so-called norms, and they typically are responded to corresponded to field length normalization factor that affects scoring. Here you can see segment info, field info, live docs bit set, per document field data, per document inverted data in segment. Here the segment info, commit metadata, segment stats, and here then you can see field info, field metadata. Field info interacts with per document field data and per term inverted data. Stored values, term vectors in document frequencies plus positions. Scoring and scoring values, norms, are in per document field data. Term dictionary plus doc frequencies, and per document term frequencies and per position attributes are in per term inverted data. Here you can see a term dictionary plus doc and frequencies. Here more descriptive, and inside it there's a per document term frequencies, and inside the per position attributes. Here you can see live docs or bit set deletions. Here you can see indexing process in here we are considering Lucene 4.0. The resulting token stream is finally processed by indexing chain. And the supported attributes, term value, position, offset, and payload data are added to the respective posting list for each term. Term values don't have to be UTF-8 strings as in previous versions of Lucene. The version 4.0 fully supports arbitrarily byte array values as terms and can use custom comparators to define the sorting order of such terms. Also at this stage, documents are assigned to their internal document identifiers, which are small sequential integers for efficient delta compression. These identifiers are ephemeral. They are used for identifying document data within a particular segment, so they naturally change after two or more segments are merged during index compaction. Here you can see the tokenizer. It's connected to field value, field 1, doc 1 are connected to here to the tokenizer. You can see term, position, offset, payload, and custom in tokenizer, and it is connected to token filters via token stream with modifiable attributes. Token filters are connected to document inverter. Here you can see the indexing chain and in-memory segment here. And a document inverter is connected to term vectors and posting list. Here you can see the term vectors, and here you can see the posting lists. Here the token filter is connected to document content via field 1 and field doc in this example. via field 1 and doc1. Now we are considering a prefix tree in spatial indexing. The spatial module is based on spatial 4.4j and Apache license library that provides implementation of various shapes such as points, rectangles, and circles, and additionally support polygons with an extra dependency. Spatial strategy is the core interface used to interact with spatial module, index spatial data, and perform spatial queries. Spatial strategy defines the way to index and query based on shapes. From Lucene Java docs, the points defined by spatial strategy as follows: can it fix more than one shape or field? What type of shapes to be indexed? What type of query shapes can be used, and what types of query operations are supported. This might vary per shape. Remember that the different shape is attempted to be indexed than what is defined by corresponding spatial strategy, and exception will be thrown. Prefix trees from the foundation of spatial index data structures in Lucene. Prefix trees act as a tree data structure where shapes are decomposed into strings. Each string representing a rectangular spatial region. This figure shows a prefix tree of words car, cat, do, and don. Car, cat, do, and don. Lucene defines an abstract class, a spatial prefix tree, which represent abstract representation of the prefix tree. This class defined all necessary methods such as getting the number of levels, getting a cell at level, and so on. There are that are required for working with prefix trees during searches. As the Lucene consists of two concrete implementation: spatial prefix tree, quad prefix tree, and geohash prefix tree. Here you can see root is connected to C, and C is connected to A, and A is connected to R, and then I is connected to end car. Here C is connected to A, and A is connected to T, and T is connected to N, is cat. And here the root is connected to D, and do is connected to D is connected to O, and O is connected to N, and it's do. And here do is connected D is connected to O, and O is connected to N, and N is connected to N, is done here. Here you can see a quad tree. A quad tree is a spatial data structure where each node has exactly 4 children. Quad tree splits a spatial dimension into 4 each time a new level is added to the tree. Quad trees are notable for 2 use properties. Higher level nodes of quad tree help representation of overall data in a less granular level. That is, a depth of detail stored in the top level is less than that stored in the leaf level nodes. Quad trees are great for searching 2-dimensional spaces. For example, given a 2-dimensional space, to find the point closest to the given coordinates, a simple traversal of quad tree will lead to the result. Here you can see a quad tree. Here root is connected to A here, and here is connected to a node, and it's another node, and this one is connected to B, C, D, and E. Here this one is connected to another node, then S, K, and L. Here this node is connected to G, H, I, and L. Oh, this one here. Here you can see a KD tree in spatial indexing. The a KD tree is a space partitioning tree that's allow splitting a plane of space into k-dimensional space. A KD tree is a binary tree which with each node representing a k-dimensional point. But put simply, given a collection of points, a range is split using an axis value. For example, if a node represents x-axis and split using x-axis is done, the left behind all the points that have an x-axis value less than the split value, the right tree having all values greater than the same one. The KD trees prove useful for a variety of query types such as point and range queries. For this reason, they are important member of Lucene's indexing capabilities. This figure shows an example of a KD tree. Lucene implementation uses block KD, BKD tree, which is an efficient version that is IO friendly and restricts IO usage. Here you can see A is connected to B and C is connected to D and D is connected to E and F. Here you can see a BKD tree in spatial indexing. BKD trees are built in the same manner as KD trees, recursing and partitioning the n-dimensional space and performing an equal split at each recursion. However, BKD trees stop recursing once there are fewer than 1024 points. At that point, all points are written to one block on the disk. When a point is indexed in the BKD tree, it is converted into an equivalent byte array representation. Lucene then buffers the points being indexed and then writes them to using a points format. All default Lucene codecs now support the points being indexed. As evident in this figure, a BKD tree is a KD tree with B tree incorporated into it. Nodes have compressed keys and their children define key ranges with equivalent pointers to their children. You can see here the BKD tree. Here you can see a Lucene 9.5 file format. Here the index structure overview. Here you can see the index structure overview in Lucene 9.5 file format. Each segment index maintains the following. Segment info. This contains metadata about a segment which has the same number of documents, what files it uses, and information about how segments is stored. Field names. This contains metadata about the set of named field used in the index. Stored value fields, stored field values. This contains each document a list of attributes value pairs where the attributes are field names. These are used to store auxiliary information about the document such as title, URL, or an identifier to access databases. The set of stored fields are what is returned for each hit when searching. This is keyed by document number. The term dictionary, a dictionary containing all of the returns, all of the terms used in all index field of all the documents. The dictionary also contains a number of documents which contain the term. The pointers to the term frequently are proximity data. Term frequency data for each term in the dictionary, numbers of all documents that contain that term, the frequency of the term in the document unless frequencies are omitted, index docs. Term proximity data for each term in the dictionary, the position of the term occurs in each document. Note that this will not exist all fields in the all document omit position data. Normalization factors, for each field in each document, the value is stored that is in multiplied into score it for hits on that field. Term vectors, each field in each document, the term vector, sometimes called document vector, may be stored. The term vector consists of terms text and terms frequency. To add the term vectors to your index, see the field constructors. Per document values, like stored values, these are also keyed by document number but are generally intended to be loaded into the main memory for fast access, whereas the stores values are generally intended for summary result for searches. Per document values are useful for things like scoring factors. Live documents, an optional file indicating the document, which document is live. Point values, the optional pair of fields recording dimensionally index field to enable fast numeric range filtering and large numeric values like big integer and big decimal, 1D and geographic shape intersection, 2D and 3D. Vector values, the vector normal format stored numeric vectors in a format optimized for random access and of computation, supporting high dimensional nearest neighbor search. Here the class Lucene 90 segment info format in package org.apache lucene.codex.lucene 90, the Lucene 9.0 segment info format. Here the class Lucene 9.94 field info format in package org.apache lucene.codex.lucene 94. Lucene 9.0 field info format. Class Lucene 90 stored field format in package org.apache lucene.codex.lucene 90. Lucene 9.0 stored field format. Class Lucene 90 posting format in package org.apache lucene.codex.lucene 90. Lucene 5.0 posting format, which encodes posting in a packed integer blocks for fast decode. Class Lucene 90 posting format in org.apache.lucene.codex.lucene 90. The Lucene 5.0 posting format, which encodes posting in a packed integer block for fast decode. Class Lucene 90 posting format in package org.apache.lucene.codex.lucene 90. Lucene 5.0 posting format, which encodes posting in a packed integer block fast decode. Class Lucene 90 forms norms format package in package org.apache.lucene.codex.lucene 90. Lucene 9.0 is core normalization format. Lucene 9.0 term vector format in package org.apache.lucene.codex.lucene 90. The Lucene 9.0 term vector format. Class Lucene 90 doc values format in package org.apache.lucene.codex.lucene 90. Lucene 9.0 doc values format. Class Lucene 90 live docs format in package org.apache.lucene.codex.lucene 90. Lucene 9.0 live doc format. Class Lucene 90 points format in package org.apache.lucene.codex.lucene 90. Lucene 9.0 point format, which encodes dimensional values in a block KD tree structure for fast 1D range and in dimensional shape intersection filtering. Lucene 95 HNSW vectors format in package Lucene.codec.lucene95. Lucene 95 vector format which encode numeric vector values and optional associated graph connecting the document having values. The graph is used to power HNSW search. The format consists of three values: .vect file, .vex file, and .vem file. Here you can see the structure, segment info, field value, stored field value, term dictionary, term frequency data, term proximity data, normalization factors, term vectors, per document values, live documents, point values, and vector values. Here you can see the summary of file extension in Lucene 9.55 format. Following table, this table summarizes the name and extension of the files in Lucene. Lucene file names by extension. Here the name segment files, extension segment underscore n. It stores information about commit point. Lock file, write.lock here. Write lock prevents multiple index writers from writing the same file. Segment info stores metadata about the segment. Compound file, an optional virtual file consisting of all the index files for systems that frequently run out of file handles. Fields stores information about the fields. Field index contains pointers to field data. Field data stored fields for documents. Term dictionary, the term dictionary stores term info. Term index, the index into the term dictionary. Frequencies contains a list of docs which contain each term along with frequency. Positions stores position information about where the term occurs in the index. Payload stores additional per position metadata information such as character offset and user payload. Norms encodes length and boost factors for docs and fields. Per document values encodes additional scoring factors or other per document information. Term vector index stores offset to the document data file. Term vector data contains term vector data. Live documents info about what documents are live. Point values hold index point. Vector values hold index vectors. .vect files contain the raw vector data and .vem the vector metadata. Example, we can consider package org.apache.lucene.index. This is a code to maintain and access indices. As an example too, we can consider this code segment here, index writer, class index writer, and index writer create and maintains an index. Here the index writer config holds all the configuration that is used to create an index writer. Once index writer has been created with this object, changes to this object will not affect the index writer instance. For that, use live index writer config that is returned from the index writer get config index writer get config. And here you can see add document method. This adds a document to index. And index close all open resources and releases the write lock. And this index writer class is in the package org.apache.lucene.index. Here you can see the class fields provides the terms index for fields that have it and list which fields do. This is primarily an internal experimental API, C fields producer, although it is also used to expose the set of term vectors per document. This is in package org.apache.lucene.index. In index reader is an abstract class providing an interface for accessing a point in time view of an index. Any changes made to index via index writer will not be visible until new index reader is opened. It is best to use directory reader.open index writer to obtain an index reader if your index writer is in process. When you need to reopen to see any changes in the index, it's best to use directory reader.open if change directory reader, since a new reader will share resources with previous one when possible. Search of an index is done entirely through its abstract interface, so that any class which implement is searchable. Here you can see the method of index reader get term vectors. This retrieves term vectors for this document, or null if term vectors were not indexed. Here access index field for an index segment, and here access term vector fields for a specified document. Here this code segment is related to terms. Terms, the class term access to terms in a specified field. Here has positions returns the true if the documents in this field store position. Here has offsets returns true if the document in this field store offsets. Has payloads returns true if the document in this field store payloads. Here the terms enum iterated to seek or step through terms to obtain frequency information for the current term. Here the iterator returns an iterator that will step through the all terms here. Here in the next here in the byte represent byte array that as a slice offset plus length into an existing byte array. The bytes member should never be null. Use empty underscore bytes if necessary. Here in next increment the iteration to the next bytes ref in the iterator, returns the resulting byte ref or null if the end of the iterator is reached. Returns the resulting byte ref and or null if the end of the iterator is reached. The return byte ref may be reused across all next across call to next. After this method returns null, do not call again. The results are undefined. Here in the term returns the current term. So here we are getting a metadata about the field here, position, offset, payload, and iterate through the terms here. and the class term is in the package org.apache.lucene.index. Here a term represents the collection of terms within a field, exposes some metadata and statistics, and the API for enumeration. Here with the documents, here you can see the post class posting enum, it's a variable, iterate through the postings. Not you must first call the doc id set iterator dot next doc before using any of the per doc methods. This is in the package org.apache.lucene.index. The posting enum is an extension of doc id select set iterator that iterates over a list of documents for a term along with the term frequency within that document. With regarding positions, here you can see a class posting enums, iterate through the postings. Not you must first call doc id set iterator dot next doc before using any of the pre-doc methods. Posting enum also allows iteration of positions. A term occurred within the document. Any additional per position information, offsets, and payloads. The information available is controlled by flags passed to term enum postings. This postum enum is in package org.apache.lucene.index. As an example 7, we can consider this one. This is from Rabbit Talk. This following index definition would allow using Lucene index for this query. Org supports Lucene based indices to support both property constraint and full text constraint. Depending on the configuration of a Lucene index, can be used to evaluate property constraint, full text constraints, or path restrictions and shorting. You can see the query here. This index definition would allow using Lucene index for this query. The index definition node for Lucene based index must be of type query index definition, must have a type property set to Lucene, must contain the async property set to value async. This is what send the index update process to background thread. Note that compared to property index, Lucene property index is always configured in async mode, hence it might lag behind the reflecting the current repository state while performing the query. Here As an example, you can see the index reader here, the class index reader. Index reader is an abstract class providing an interface for accessing a point in time view of an index. Any changes made to the index via index writer will not be visible until new index read is opened. It is best to use in directory read dot open index writer to obtain an index reader if your index writer is in progress. When you need to reopen to see changes in the index, it's best to use directory reader dot open open if change directory reader, since the new reader will share resources with the previous one when possible. Search of an index is done entirely through this abstract interface, so that any subclass which implement is searchable. This is in package org.apache.lucene.index. This is open existing index here. As an example, now we are considering index writer in index APIs in package org.apache.lucene.index. Index writer is used to create an index and to add, update and delete documents. The class index writer in package org.apache.lucene.index, and index writer creates and maintains an index. Index writer is used to create an index and to add, update and delete documents. The index writer class is thread safe and enforces a single instance per index. Creating an index writer creates a new index or open an existing index for writing in a directory depending on the configuration of index writer config. A directory is an abstraction of typically represent a local file system directory. Various implementation of FS directory, but it may also stand for some other storage such as RAM. Now we are considering field types. Stored field values are retrieved by a searcher using implementation of stored field visitor. Class stored field visitor in package org.apache.lucene.index provides a low level means of accessing the stored field values in an index. Lucene supports a variety of different documents field data structures. Lucene's core and inverted index is comprised of postings. The posting with their term dictionary can be thought of as a map that provides sufficient efficient lookup given a term, roughly a word or token, to ordered a list of documents containing that term codex. Additionally, record impacts alongside posting in order to be able to skip over low scoring documents at the search time. Posting do not provide any way of retrieving terms given a document short of scanning the entire index. Stored fields are essentially the opposite of postings, providing efficient retrieval of field values given a doc ID. All stored field values for a document are stored together in a block. Different types of stored field provide high-level data types such as strings and numbers on top of underlined bytes. Stored field values are usually retrieved by searcher using implementation of stored field visitor. Doc values field are what are sometimes referred to as columnar or column style fields by analogy to relational database terminology, in which documents are considered as rows and fields and columns. Doc values fields store values per field. The value for every document is held in a single data structure, providing for rapid sequential lookup of a field given a doc ID. These fields are used for efficient value-based sorting and for faceting, but they are not useful for filtering. Point values represent numeric values using a KDT data structure. Efficient one and higher dimensional implementation make these the choice for numeric range and interval queries and geospatial queries. Now we are considering fields in postings API. Field is the initial entry point into the posting API. This can be obtained in several ways. The class fields in package org.apache.lucene.index provide a terms index for fields that have it and list which fields do. This is primarily an internal or experimental API, although it is also used to expose the set of term vectors per document. Here the fields implement Java iterable interface. So it's easy to enumerate a list of fields here. Here the access index fields for index segment. Here the access term vector fields for specified document. So enumerate a list of fields. Access the terms for this field. Here you can see terms. The terms represents collection of terms within a field, exposes some metadata and statistics and API enumeration. The class terms in package org.apache.lucene.index access to the terms in a specific field. Here the term enum provides an iterator over the list of terms within a field. Some statistic about the term and methods to access terms, documents, and positions. Here the metadata about the field. Here the iterate through term. Seek the specific term. Get the document frequency and enumerate through the documents, and enumerate through the documents and position. The documents now, the posting enum is an extension of docid settled iterator over the list of documents for a term along with the term frequency that within that document. Here the class posting enum in package.apache.lucene.index iterates through the postings. Note that you must first call the docid iterator set iterator.nextdoc before using any of these pre-doc methods. Posting enum is an extension of docid iterator that iterate over the list of document for a term along with the term frequency within that document. Positions postings enum also allows iteration of postings a term occurred within a document or any additional per position information, offset, and payload. The information available is controlled by flags passed to the terms enum postings. Now we are considering term statistics in index statistics. Term enum.docfreq method returns the number of documents that contain at least one occurrence of the term. This statistics is always available for an index term. Note that it will also count deleted documents when segments are merged. The statistics is uploaded as this deleted document are merged away. Term enum.total term freq method returns the number of occurrences of this term across all documents. Like docfreq method, it will also count occurrences that appear in the deleted documents. Now we are considering introduction in Apache Lucene index file format in package apache.lucene.codex.lucene95. This here we are define the index file format used in this version of Lucene. If you are using different version of Lucene, please consult the copy of the docs that was distributed with the version you are using. Now we are considering definition document numbers in definition. In particular, numbers may change in the following situations. Internally, Lucene refers to documents by an integer document number. At first, the document added to an index is numbered 0, and each subsequent document added gets a number 1 greater than the previous. Note that the document number may change, so caution should be taken when storing these numbers outside the Lucene. In particular, numbers may change in the following situations. A number is stored in each segment are unique when within the segment, and must be converted before they can be used in a larger context. The standard technique is to allocate each segment of range values based on the range of numbers used in the segment. To convert a document number for a segment from segment to external value, the segment-based document number is added. To convert an external value back to the segment-specific value, segment is identified by the range that external value is in. The segment base value is subtracted. For example, 2.5 document segment might be combined so that the first segment has the base value of 0 and the second of 5. Document 3 from the second segment would have been an external value of 8. When the documents are deleted, gaps are created in the numbering. These are eventually removed as the index evolves through merging. Deleted documents are dropped when segments are merged. A freshly merged segment has thus no gaps in the numbering in its numbering. Now we are considering file naming. All files belongs to a segment have the same name with the varying extensions. The extensions correspond to a different file formats. When using a compound file format, default for all small segment, these files except for the segment info file and log file and deleted document file are collapsed into a single .cfs file. Typically, all segments in an index are stored in a single directory, although it is not required. File names are never reused. That is, when any file is saved to the directory, it is given a never before used file name. This is achieved using simple generations approach. For example, the first segment file is segment _1, then segment _2, etc. Generation is a sequential long integer represented in alphanumeric base 36 form. Now we are considering log file. If the directory is different from the index directory, then the write log will be named xxx-write.log, where xxx is a unique prefix derived from full path to the index directory. The write log, which is stored in the index directory by default, is named write.log. If the log directory is different from the index directory, then the write log will be named xxx-write.log, where the xxx is a unique prefix derived from the full path to the index directory. When this file is present, a writer is currently modifying the index, adding or removing documents. This log file ensures that only one writer is modifying the index at a time. Now we are considering Lucene 9.7.0 Facet API. Lucene 9.7.0 Facet API provides facet indexing and search capabilities. Now we are considering index time joins in Lucene 9.7.0 join API. It's Lucene's join module. This query should be used after main query has been executed. For each hit, execute the parent children block join query. The class parent children block join query in package of Apache lucene.search.join. This query that returns all the matching child documents for a specific parent document indexed together in the same block. The provided child query determines the matching child docs is being returned. The index time joining supports joins while searching, where joins document are indexed in a single document block using index.add documents. This is useful for any normalized content, XML documents or database tables. In database terms, all rows for a join table matching a single row is the primary table must be indexed as a single document block. With the parent document being last in the group. When you are indexing this way, document in your index are divided into parent document, last document for each block, the child document, all others. You provide a bits set provider that identify the parent document, as Lucene does not currently record any information about doc blocks. At search time, the two parent block join query to remap join matches from any child query, that is a query that matches only child document up to the parent document space. Resulting query can be then used as a clause in any query that matches parent. If you care about what child documents matched for each parent document, then the parent children block join query to per matched parent document retrieve the child document that caused to match the parent document first place. This query should be used after main query has been executed. For each it executes the parent child children block query. So to map or join in the position direction, use to child block join query, which wraps any query matching parent document, creating the joint query matching only child index. So this is basically with Lucene search module, but I included this here as an example due to the indexing. Do you see the importance of indexing here? Run the parent block join query to figure out top matching children nodes. Process top child hit. Now we are considering Lucene 9.7 memory API. Here the class memory index in package Lucene.index memory, high performance single document main memory Apache Lucene full text search index with the package, and the memory API is for the memory. And the class memory index, that's high performance single document main memory Apache Lucene full text search index. Here you can see an example usage. This class is a replacement. Here the memory index is a replacement subject for RAM resident directory implementation. It is designed to enable maximum efficiency for on-the-fly matchmaking, combining structure and fuzzy full text search in the real-time streaming applications such as NuxX query-based XML query, XML message queues, public subscribe system for blog newsfeed, text chat, data acquisition and distribution systems, application level routers, firewall and classifiers, etc. Rather than targeting full text search in infrequent queries over huge persistent data achieved historic search, this class target full text search of a huge number of queries over comparatively small transient real-time data, prospective search, for example as in here. The instance can hold the most Lucene document. with the document containing 0 or more fields, each field having this um, name and full text value. Full text is tokenized, split and transformed into 0 or more index terms, also known as words on add field, according to the policy implemented by the analyzer. For example, Lucene analyzers can split on white space, normalize to lower case for case sensitivity, ignore command terms with the little discriminatory value such as he, in, and stop words, reduce the term to their natural linguistic root from such as fishing being reduced to fish, stemming, resolve synonyms, inflections, the tertiary upon indexing and or querying, etc. Abstract Lucene queries can be run against this class. Note that the Lucene query select on the field names and associated index tokenized terms, not on the original full text. The latter are not stored but rather thrown away immediately after tokenization. Now we are considering class index splitter in package of.apache lucene.misc.index. Here we are considering Lucene 9.7.0 miscellaneous API. Miscellaneous tool. The MAIC package has various tools for splitting, merging dishes, changing norms, finding high-freq terms, and others. With the class splitter, index splitter, command line tool that enables listing segments in an index, copying specific segment to another index, and deleting segments from index. Now we are considering Lucene 9.7.0 replicate API. The provides index files replication capabilities. Here an example usage of replicator. The interface replicator is in package of.apache lucene.replicator deprecated. Use doc.apache lucene.replicator.nrt instead. An interface for replicating files allows a user or allows a producer to publish revisions and consumers to check the updates when the client needs to be updated. It is given a session token through which can obtain the files of that revision. After the client has finished obtaining all the files, it should release the given session so that the files can be reclaimed if they are not redeemed, if they are not needed anymore. Files, this is a file replication. Here this package is a file replication framework. A replicator allows republishing replicating files between server and client. Producer publish revisions and consumes update to the latest revision available. Replication client is the helper utility for performing update operation. It can be invoked either manually or periodically by starting an update thread. HTTP replicator can be used to replicate revisions by consumers that reside on a different node than the producer. The replication framework supports replicating any type of files with the built-in support for single search index. An application should publish an index revision and the index replicator handler to the client. On the client. For an index and taxonomical pair, the application should publish an index and taxonomical revision and set index and taxonomical replication handler on the client. When replication client detects that there is a new revision available, it copies the files from the revision and then invoke the handler to a complete operation. For example, copy the files to the index directory, fsync, then reopen and index read, etc. By default, only files that do not exist in the handler current revision files are copied. However, it can be overridden by extending the client. Example usage of the replicate is here. So here the server side, writer used for indexing. Client side, either local replicator or HTTP replicator if the client and server are on different nodes. Callback invoke after handler finish handling a revision and, for example, can reopen the reader. Can also be null if no callback is needed. Invoke a client manually or periodically. Check for update every 100 milliseconds. We are now considering tools. Type this command to launch Luke. Lucene Toolbox GUI tool, a swing app for browsing documents, is index terms and posting list, searching an index and so on. Type this command to launch Luke. Well, we can consider index format to old exception, the class. This exception is thrown when Lucene detects an index that is too old for this Lucene version. This is in package org.apache.lucene.index. As an error example, we can consider this one. Java IO exception, no subfile, sub-file with id.fnm found, etc. And here com.library.portal.search.lucene index writer.update document, etc. And here the org.apache.lucene.index.field infos, etc. And here you can see the compound file reader also. Now we are focusing on Lucene storer. org.apache.lucene.store defines an abstract class for storing persistent data, the directory, which is a collection of name files written by an index output and read by an index input. Multiple implementations are provided, but FS directory is generally recommended as it tries to use operating system disk buffer caches efficiently. Here you can consider a package org.apache.lucene.store binary IO API used for all index data. Here you can see the fs directory class, base class for directory implementation that store index files in the file system. Here method public static fs directory open path creates an fs directory instance trying to pick the best implementation given the current environment. The directory returned uses the native fslog factory. The directory is created at the named location if it does not yet exist. This class is in package org.apache.lucene.sto. As an example 3, we can consider lucene.store.type equal jdbc. This is in Sun Glassfish web space server 10.0. There is a single property called lucene.store.type. By default, this is set to go to the file system. You can change this to this so that the index is stored in the database by making it the following here. As an exception example, we can consider class lock obtain failed exception. This exception is thrown when the write.lock could not be acquired. This happens when a writer tries to open an index that another writer already has open. This is in package org.apache.lucene.sto. As an exception example, we can consider lock obtain failed exception. Class lock obtain failed exception. This exception is thrown when the write.lock could not be acquired. This happens when the writer tries to open an index that another writer already has open. This is in package org.apache.lucene.sto. As an error example, we can consider this one, java.line.error. Unresolved compilation problems. Directory cannot be resolved to a type. The main method open path in the type fs directory is not applicable for arguments file. Now we are focusing on indexed files. An index file is a computer file with an index that allow easy random access to any record given its file key. Here you can see a detailed look inside the Lucene's index format. Here .fnm, the fields, stores information about fields here, and .tis, term infos, part of the term dictionary stores term info, and here .frq, frequencies, contains a list of docs which contains each term along with frequency, and .prx, positions, stores position information about where a term occurs in the index. Here in the inverted index, Lucene uses a well-known index structure called inverted index. Quite simply, and probably unsurprisingly, the inverted index is an inside-out arrangement of document in which terms take center stage. Each term refers to documents that contained it. Let's dissect a sample book data index to get a deeper glimpse at the files in the index directory. Regardless of whether you are working with a RAM directory or FS directory or another directory implementation, the internal structure is a group of files. In a RAM directory, the files are virtual and live entirely within RAM. An fs directory literally represents the index of a file system directory as directory. The compound file mode adds an additional twist regarding the files in a directory. When an index writer is set to for a compound mode, the files are written to a single .cfs file, which alleviates the common issue of running out of file handles. Our summary glosses over most of the intricacies of data compression used in the actual data representation. This extrapolation is helpful in giving you a feel for structure instead of getting caught up with miniature, which again are detailed on Lucene's website. This figure represents a slice of a sample books index. The slice is a single segment. In this case, we have an optimized index with only single segment. A segment is given in a unique file name prefix _c in this case. Here field names .fnm. The .fnm file contains all the field names used by documents in the associated segment. Each field is flagged to indicate options that were used while indexing. Is it indexed? Does it have a term vector enabled? Does it store norms? Does it have payloads? In order of the field names, the order of the field names in the .fnm file is determined during the indexing and isn't necessarily alphabetical. Each field is assigned a unique integer field number. Each field is assigned a unique integer, the field number, according to the order in the file. In this file, that field number instead of string name is used in other Lucene files to save space. All terms, this is a term dictionary .tis or .tii file. All terms, tuples of fields, field name and value in a segment are stored in the .tis file. Terms are ordered first alphabetically. According to the UTF-16 Java character by field name and then by the value within the field. Each term entry contains its document frequency. The number of documents that contain this term within the segment. In this figure shows only the sampling of the terms in our index, one or more from each field. Not shown is the .tii file, which is a cross-section of the TIS file designed to be kept in the physical memory for random access to the TIS TIS file. For each term in the TIS file, the the .frf file contains entry for each document contained in the term. Here in our sample index, two books have the value JUnit in the content field. Term frequencies. The term frequencies in each document are listed in the fr.frq file. In our sample index that, for example, ant in action document ID 5 has the value JUnit once in the content field. JUnit in action second edition has the value JUnit twice, provided once by the title field and the once by the subject field in this example. Our contents field is the aggregation of title, subject and author. The frequency of a term in a document in a document factors into score calculations and typically boosts a document relevance for higher frequencies. For each document listed in the .frq file, the positions.prx file contains entries for each occurrence of the term within the document. The term positions, the .prx file lists the positions of each term within the document. The position information is used when queries demanded it, such as praise queries and span queries. Position information for tokenized fields comes directly from the token position increment designated during analysis. This file also contains payloads, if any. In this figure shows three positions for each occurrence of the term JUnit. The first occurrence is in document 5 in position 9. In the case of documents 5, the field value after analysis is ant action, Apache, Jakarta, ant build, tool, Java, doc development, JUnit, Eric, Hatcher, Steve, Logan. We use the standard analyzer, thus step word in ant in action, for example, are removed. Document 6, JUnit in action second edition has contents field containing the value JUnit twice, once position 1 and again position 3. Stored fields. When you request that a field to be stored, field.store.ts, it is written into two files, the .fdx file and the .fdt file. The .fdx file contains simple index information which is used to resolve document number to extract position in the .fdt file for the document's stored field. The .fdd file contains the contents of the fields that were stored. Term vectors. The term vectors are stored in three files. The .tvf file is the largest and stores specific terms stored alphabetically and other fields. Other frequencies plus the optional offsets and positions for the terms. The .tvd files list which fields had term vectors for a given document and indices byte offsets into the .tvf file so specific fields can be retrieved. Finally, the .tvx file has index information which resolves the document numbers into the byte positions in the .tvf and tvd files. Norms. The .nrm file contains normalization factors that represent the boost information gathered during indexing. Each document has one byte in this file, which encodes the combination of documents boost, that fields boost, and normalization factor based on the overall length of the content that in that field. Deletions: if any deletions have been committed to the index against document content in the segment, there will be a .del file present, name _x_n.del, where x is the name of the segment and n is the integer that increments every time new deletes are committed. This file contains a bit vector that's set for any deleted documents. Here you can see the index structure in here. Here the index, an index is basically a set of documents that are to be searched. The index may be composed of multiple sub-indexes, so segments. Each segment is a fully independent index which could be searched separately. Fields: when a document is added to an index, different sections of the document are identified and given a common name called fields. For example, document title, document body, hyperlinks, the document URL, etc. Terms: the words in the field are extracted and are stored in the index as terms. A term, basically a string extracted from the document. The same string in two different fields is considered different term. Terms are represented as a pair of strings, the first naming the field and the second naming the text within the field. Stored or indexed: the Lucene fields may be stored, in which case their text is stored in the index literally in a non-inverted manner. Fields that are inverted are called indexed. The fields may be both stored and indexed. Tokenized or non-tokenized: the text of the field may be tokenized into terms to be indexed, or the text of a field may be used literally as term to be indexed. Most fields are tokenized, but sometimes it is useful for certain identifier fields to be indexed literally. Lucene uses file extensions to identify different parts of the index. Here you can see the index structure. Here we are considering Lucene 3.4. Here segments are in index. Segment consists documents here. Documents are in segments. Here the fields are in a document, and here the terms are in field. Here you can see the now we are considering field information .fnm. Field info file with the suffix fnm records the index time attributes and field names for every field. Fields are numbered by their order in this file. Thus the field 0 is the first field in the file. Thus the field 0 is the first field in the file. Field 1 the next, and so on. Note that the document numbers, field numbers are segment relative. Here you can see FNM version vint indexes version from 2.9 to 3.3 is -2, and indexes version for more than 3.4 plus is -3. Next you can see the field count vint, and next field name field bits. Here field name is string. In this this section consists of field name string and field bits byte. Here the bit 8 is 1 equal positions are omitted for the index field. Bit 7 1 equal term equal frequencies and positions are omitted for the indexed field. Bit 6 1 equal payload are stored for the index field. Bit 5 the 1 equal norms are omitted for the index field. Bit 4 1 equal terms offsets are stored with the term vectors. Bit 3 1 equal term positions are stored with the term vectors. Bit 2 with term vectors equal 1 and without term vector equals 0. Bit 1 indexed field equal 1, non-indexed field equals 0. So this bit 8 to bits 1 are in field bits byte. The field name string and field bit string are in this section. Here you can see stored fields. Stored fields are the original raw text values that were given in Lucene. This is not really a part of inverted index structure. It's simply a mapping from document ID to stored field data. Stored fields are represented by two files. The field index or FDX file that contains for each document a pointer to its field data. The field data or FDT file. This contains the stored fields of each document. Here you can see the field index of FDX file .fdx. Here the offset equal doc id multiplied by htail uint 64 size. Here the field value position here the field value position segment size. Here the field value position uint 64. Doc id is field value. It is connected to field data or FDT file. This should be FDT here. Here you can see document field data segment size here, and here the before that here you can see field count vint and another field, and then here you can see field number vint, and in this section consists of field number vint and bits vbyte, and it consists bit 8 bit 8, and here the bit 7 to bit 6, so yeah, bit 7, and here the bit 6 to and bit 5 and bit 4 is 001 value is an int, and 010 equal value is a long, 0 1 1 is equal value is int as float, and 1 0 0 the value is long as double. The bit 3 is in bit 3 one equal field has compression option enabled, only available for version less than or equal 2.9.x. Bit 2 one equal field contains binary data. Bit 1 tokenizer field equal 1 and non-tokenizer field equal 0. So it will be here bits and bits byte. Here the value string or binary value or int long depending on bits 4 to 6. With the binary value here, value size v inc. Here the here the value size binary value, the value size v int, and byte is value size. Here the field name, bits and value here with the field count here, and then this section represents this area, and then the document field data segment size here. Now we are considering here you can see the term dictionary. The term dictionary stores how to navigate the various other files for the each term. At simple high level, the term dictionary will let you where to look in the FRQ and PRX files. For further information related to that term, terms are stored in an alphabetical order for fast lookup. Further, another data structure, the term info index is designed to be read entirely into memory and used to provide random access to the TIS file. Other bookkeeping, skip test, skip list and index intervals also tracked with the term dictionary. Term infos.tis, the term infos file.tis contain all terms in a segment ordered by field name, then the value within the field, it also contains document frequency for each term. Inverted index, so how many documents contain that term. Term info index TII .tii. This contains every index interval entry from the TIS file along with its location in the TIS file. This is designed to be read entirely into memory and used to provide random access to the TIS file. The structure of this file is very similar to the TIS file, with addition of one item per record in index delta. index interval. In order to accelerate the searching of a term, Lucene uses multi-level skip list. The index interval is the interval at which the terms are saved in the .tii file. For example, assuming index interval equal 4, the dictionary index tii file will save 4th, 8th, 12th term, which can speed up the dictionary lookup in TIS. Skip interval is the fraction of term docs stored in skip tables. It is used to accelerate term docs .skip to int. Larger values result in small indexes, greater acceleration, but few accelerable cases, while smaller value result in a bigger indexes, less acceleration in case of small value for max skip levels, and more accelerable cases. Max skip levels in the max number of skip levels stored for each term in the .frq file. A low value result smaller indexes but less acceleration. A larger value result in slightly large indexes but great acceleration. See format of .frq file for more information about skip levels. Prefix length. The term text prefixes are shared. The prefix length is the number of initial characters from the previous term, which must be pretended to a term suffix in order to form the term's text. Thus, if the previous term's text was born, then the term is boy. The prefix is prefix length is 2 and the suffix is y. Document frequency. Docfreq is the count of the document which contain the term. Frequency delta. Freq delta determines the position of this term's term freq within the .frq file. In particular, it is the difference between the position of terms data in that file and the position of the previous term's data, or 0 for the first term in the file. Proxy delta. Prox delta determines the position of this term position within the .prx file. In particular, it is the difference between the position of the term's data in that file and position of the previous term's data, or 0 for the first term in the file. Skip delta determines the position of this term's skip data within .frq file. In particular, it is the number of bytes of the term freq and that the skip data starts. In other words, it is the length of the term freq data. Here you can see the term infos .tis. Here the TI version, uint 32, term count uint 64, index interval uint 32, skip interval uint 32, then max skip levels uint 32. Here term info, and then after gap term infos there. Here index intervals, one index interval here and then another index interval. Here this is index interval. Here term infos, term count. Term info consists of term, doc frequency, vint and frequency delta vint, proxy delta vint, and skip delta vint. Term consists of prefix length vint, suffixed string, and field name vint. The term info index dot tii, ti version uint 32, index term count uint 64, index term count equal term count divided by index interval here term count L, index interval u int 32, then the skip interval u int 32, max skip levels u int 32, term index and term index, and there are term indexes, and this is term index count from this area. Term index consists of term info and index delta or v long. Here the term index is connected to term info here. Here the term index is connected to term info here, and term index connected to term info here. So term indexes are connected to term infos in term infos. Now here you can see term frequencies dot frq in Lucene 3.4 here. The dot frq file contains the list of document which contain each term along with the frequency of term in that document. This file contains the term posting list. This file contains the term posting list asterisk term count entries. Each entry is a posting list corresponding to a term. Each posting list consists of a term frequency and a skip list. Term frequency consists of a list of doc deltas and the number of times this term occurs in that doc. The doc delta encodes both the document number and the frequency. In particular, doc delta divided by 2 is the difference between this document number and the previous document number, or 0 when this is the first document in a term freq. When doc delta is odd, the frequency is 1. When the doc delta is even, the frequency is read as another vint. If omit tf equal false, store the term frequency. For example, if the term occurs once in the document 7, doc id equal 7, the freq equal 1, and 3 times the document 11, doc id equal 11, and freq 3, we would get the following sequence of vint 15, 8, and 3. Here's how it is calculated. In order to save space, Lucene does not store the doc IDs as is. Instead, it calculates the delta as a delta. Doc ID delta equals 7 and frequency equal 1. Doc ID delta equal 4, frequency 4, 11 minus 7, and frequency equal 3. For this first term, since the frequency is 1, the frequency information is encoded in the delta itself. Doc ID delta equals 7 and the binary is 0000111. Since we want to store the frequency of 1 in doc delta, the last bit of the doc delta is 1, doc ID is odd, so we know that the frequency is encoded in the doc delta and freq equal 1. For the second term, since the frequency is more than 1, we use the separate vint to calculate the frequency. Doc ID delta equal 4 in the binary 00000100. Since we want to show the following int is for frequency and not another doc ID, we need to make the last bit 0. Then shifting left for and 1 by real frequency equal 3 then. So to get the sequence, doc delta equal 15, doc delta equal 8, freq 3, namely sequence 1583. If omit tf equal true, skipping storing term frequency. If the omit tf were true, it would be this sequence of vint instead 7 4. If we omit term frequency, then all we are storing is the doc deltas. The doc deltas are therefore doc ID 7, doc ID 11 equal to doc ID 7, doc ID 11 minus 7 is 7 and 4. Skip data. The skip data contains a set of skip lists that allow us to find term frequency, doc delta, freq quickly. Number of skip levels in skip data equal num skip levels. Equal min skip data equal num skip level equal mint max skip levels flow log doc divided by log skip level. Doc frequency equal doc count that contains the term item. Number of nodes in and each skip level equal doc freq. Number of nodes in each skip level is equal doc freq divided by skip interval to the power level plus 1, level equal level greater than or equal 0. All the skip levels are appended together, preceded by the skip level length. The last level does not need skip level length since there are no more levels below it, so it is skipped. All skip datum in all levels except the last level have a skip child level PTR. which point to the next skip level. Each skip datum skip node contains the following information: document number, payload length, freak skip, proxy skip, and skip child level PTR. Here you can see term frequencies.frqs file. Here the term frequent skip and skip data with term count here, and here the this one consists of term freak, doc freak, and here the skip data. Here the term freak consists of doc delta vint and frequent, then frequency vint. Here the skip data consists of skip level, skip level length and skip level, num skip level -1, and skip level and skip datum. Here the skip level length vint and skip level, and it's connected to a skip level and skip datum here. Doc freak divided by skip interval to the power level +1 here. Here the skip level and skip level is connected. This is skip level here. Here the skip datum. It consists of doc skip vint, payload length vint, is freak skip vint, proxy skip vint, skip child level pointer vlong, and here it's connected to here the skip data. Here the you can see the frequencies file with the skip list here. For example, if the skip interval is 4, equal max skip levels 2, and doc frequency is 35. The skip level 0 has 8 skip data entries. Equal 35 divided by 4 to the power 0 plus 1, containing the 3rd, 7th, 11th, 15th, 19th, 23rd and 27th and 31st document numbers in term freaks. Skip level 1 has 2 skip data entries, equal 35 divided by 4 to the power 1 plus 1, containing the 15th and 31st document numbers in term freaks. Thus for skip level 4, and when there are 35 documents, skip level 0 should include documents 3, 7, 8, 3, 7, 11, 15, 19, 23, 27 and 31, and skip level 1 should include 15, 31 documents. But in the real implementation, we store the previous docs as shown here. Here you can see doc freak 35 and skip level 4, and this is doc list, and here the skip level 0 and here skip level 1. Here the term here the frequencies .frq, term freak skip data term count here the freak term freak and skip data, and here doc freak, and this is a term posting list. Here the term freaks are there, and in the end here the skip data, and term freak has doc delta vint and frequency vint term freak, and here the skip data skip level length skip data datum equal 14. Here the skip datum equal 30, skip datum 2, skip datum 6, skip datum 10, skip datum 14, skip datum 18, skip datum 22, skip datum 26, skip datum 30. Here mappings, and skip datum 2 here. And here skip level 1, and here skip level 2. Skip level is equal 0 here. Here the skip level 22 skipped datum, doc skip vent, payload length vent, freak skip vent, proxy skip vent, and skip child level pointer vlog. Here the now we are considering position location data.prx. The .prx file contains a list of positions that each term occurs at within the document. If omit tf is set to true in a field, no entry for that term will be stored in this file. If the omit tf is set for all terms, then the .prx files will not exist. The position delta is the is the difference between the position of the current occurrence in a document and the previous occurrence, or 0 if this is the first occurrence in the document. For example, term positions for a term which occurs at the 4th term in one document and as the 5th and 9th term in the subsequent document, the document would be the following sequence of vent 454. Payload in Apache Lucene is an arbitrary byte array stored at a specific position. That is a specific token divided by term in the index. A payload can be used to store weight for specific terms, so things like part of speech tags or other semantic information. Payload length is the length of the payload data. If there is no payload length but the payload data is found, its length is the same as the previous payload. Position file .prx, here the term positions, term count. Term positions consist of here term positions, here the positions, here the position doc freak, and position consist of positions consist of position, here the position freak. Position consists of doc position delta, vent, and payload, and payload consists of payload length, vent, payload data, bytes, and here the frequencies file .frq. Skip level length. This is skip level 1 here. Skip level datum 14. Skip level skip datum 30, and here the skip level 0 as an example. Skip datum 2, skip datum 6, skip datum equal 10, skip datum equal 14, skip datum is equal 18, skip datum is 22, skip datum is 26, skip datum is 30. Here the in this example here the position, this position is connected to skip datum 2, and this position is connected to skip datum 6, and sorry, this skip datum 2 is connected to skip datum positions here. Skip datum 6 position is connected to position here. Skip datum is 14 is connected to position here. And here the skip datum 14 is connected to skip datum 14 is here, and skip datum 30 is connected to skip datum 30. Here you can see the .kdd in filed in Lucene 8.6.0. The data structure of .kdd is here. Leaf node data describe the information of a leaf nodes. You can see there is only leaf node data in .kdd file, and the default maximum number of points in each left node data is 512 and 512. Here you can see the .kdd file structure, header, then fields, then footer. The field consists of left node data, leaf node data, and leaf node data and the data segments. Here you can see a leaf node data. The count describes the number of points in leaf node data. Doc IDs describe the set of document IDs which point in a leaf node data belongs to. Point values describe a set of point values. Each point value is split into point values describes a set of point values. Each point value is split into two parts: common prefixes and block packed values. Here you can see a leaf node data consists of count, doc IDs, and point values. Here you can see the common prefixes. Common prefixes describe a set of common prefixes with each dimension. Length value, the value describe the common prefix value with the byte, and the length means the length of a common prefix value, number of bytes. Here you can see common prefixes consist of dimensions, first, second, n dimension, and each dimension consists of length and a value. Here you can see here .kdi in Lucene 8.6.0. The data structure of .kdi file is here. Here the packed index value describes the information of all inner nodes, also known as branch node. Inner node has 4 types of data structure according to the position in KD tree and its subnode. Right node has leaf child. Inner node, that is the right that the inner node is the right node of its parent node, and its child node are leaf nodes. Right node has not leaf child. The inner node is the right node, and its parent node and its child nodes are not leaf nodes. Left node has leaf child. The inner node is the left node, and its parent node and its child node are leaf nodes. Left node has not leaf child. The inner node is the left node, and it's of its parent node, and its child nodes are not leaf nodes. Root node as the inner node, and it belongs to right node, has not leaf child. Here you can see it consists of this .kdi consists of header and fields and footer. Each field consists with packed index value. Here you can see right node has not leaf child. Here the left leaf block FP describes the pointer where the position of the leftmost node leaf node of the current inner node in the .kdd file is. Code describes the metadata about inner node, such as split dimension or byte per dimension, how many bytes each value in each dimension takes. Split value, in this stage the constructing a KD tree, that set of points in inner node will be split into two subnodes according to split value, which is a value of one of the dimension. Left num byte describe the total size of one inner node's left subtree. Here inner node has not left child, consists with left leaf block FP code split value and left num bytes. Here you can see right node has not leaf child. Left is in the here the left leafed block FP here the left leaf block FP code and split value describes the same meaning. Right leaf block FP describes a pointer where the position of the right leaf node of the current inner node in .kdd file is. Here the right node has left child, consists with left leaf block FP code split value and right leaf block FP. Here you can see left node has leaf child. You can see the code split value and right leaf block FP describe the same meaning. The left node has leaf child consist code split value right leaf block FP. Here you can see the left node has not leaf child. Code split value and left num bytes describe the same meaning. Left node has not leaf child, consists code split value left num bytes. Here the you can see the here you can see the KD tree and index values, index file. Inner node in a KD tree would be stored in .kid file as below. KDI file as below. Here you can see the root node and it's connected to inner nodes, and this node is connected to other inner nodes, and this is these are leaf nodes. Here the root node is connected to right node has not leaf child. Then the this inner node is connected to left node has not leaf child. This inner node is connected to left node has leaf child, and this one is connected to right node has leaf child, and this inner node is connected to right node has not leaf child. Here the left node has leaf child and the right node has leaf child. Here the this section makes a packed index value in .kdi in packs index value which is a field in .kdi file. Here you can see header and fields and the footer. Here you can see the leaf node in leaf node in .kd tree would be stored in kdd file as below. As here you can see a root node, and you can see inner nodes here, and then these are leaf nodes here. Here this leaf node is connected to left node data, and this one is connected to left node data. This one is connected to leaf node data, and this is connected to this leaf node data, and these leaf nodes are connected to leaf node data here, and this segment is this segment is a field in .kdd file. You can see header here and fields here and footer here. Here you can see the left num bytes. The left num bytes describe the total size of one inner node's left subtree. It makes a reader can skip to the position of inner node's right node in .kid file, and its left node is just in the next position. Here you can see a root node, and these are inner nodes, and you can see leaf nodes here. Here the root node is connected to left node has not leaf child, and it consists of left leaf block fp code, split value, and left num bytes. Left num bytes are here, there, here. Here this node is connected to leaf node has not leaf left node has not leaf leaf child. This one is connected to this inner node is connected to left node has leaf child, and this inner node is connected to right node has leaf child, and this one is connected to this inner node is connected to right node has not leaf child, and this inner node is connected to left node has leaf child, and this inner node is connected to right node has leaf child. And here the left num bytes is covered this size, the left num bytes here for the tree here. Here you can see the root node is connected to right node has not leaf child, and this inner node is connected to left node has not leaf child. This consists code, split value, and left num bytes. So it's covered this left here the left num bytes here, this section, and here the inner node is connected to leaf node has leaf child, left node has leaf child, and here this inner node is connected to right node has leaf child, and this one inner node is connected to right node has not leaf child, and inner node is connected to left node has leaf child, and inner node is connected to right node has leaf child. Here you can see left leaf block fp and right leaf block fp in Lucene 8.6.0 here. By left leaf block fp, and right leaf block FP leaf nodes can be positioned in .kdd file. Here you can see the root node is connected to right node has not leaf child and is consist of leaf left lead block FP code split value and left num bytes, and it is connected to then here the left leaf block FP is connected to here the left leaf node data here. And here the here you can see this inner node is connected to leaf node has leaf child. Sorry, left node has leaf child and is code split value, and right leaf block FP is connected to this one here, this leaf node data here. Here you can see the this inner node is connected to right node has leaf child, and here you can see left leaf block FP code split value and right leaf block FP. Here the left leaf block FP is connected to this leaf node data, and here the right leaf block FP is connected to leaf node data here. Here you can see the .kdm is the data the data structure of .kdm file. Data structure of .kdm file is here you can see here the -1 is a fixed padding value. In this stage the reading in the stage of reading .kdm file, it has a mark it as a mark means the means all fields has been read. Here you can see .kdm file consists of header and fields and -1 here, and kdi file length and kdd file length and footer, and field consists of field number and index. Here you can see kdi file length and kdd file length. In this stage of reading .kdm index file, kdi file length and kdd file length used to validate kdi and kdd files such as truncated file or file too long. Here you can see the .kdm file. It's it consists of header and fields and -1 kdi file length and kdd file length and footer. Here kdi file length is connected to kdi file length here, header the length of with header and fields and footer here in kdi, and kdd file length is connected to the kdd file length in file length in .kdd with header, fields and footer. Here you can see in index here you can see the index in .kdm. Here you can see the header. It consists of header, num data dims, num index dims, count per leaf, bytes per dim, num leaves, min packed value, max packed value, point count, doc count, length, data start fp, index start fp. Here you can see the index in .kdm here. Here num data dims describe how many dimensions we are storing at the leaf data nodes. Here the num index dims describe how many dimensions we are indexing in the internal nodes. Here count per leaf describe the maximum number of points in each leaf node. Byte per dim describe the number of bytes per dimension. Num leaves describe the number of leaf nodes. Min packed value describe the minimum value for each dimension, and max packed value describe the maximum value for each dimension values. Point count describe the total number of index points across all document. Doc count describe the total number of documents that have index at least 1 point. Length describe the size of packed index value. Data start fp describe the pointer where the beginning position of current field data in .kdd file is, and index start fp describe the pointer where the beginning of position of current field data in .kdi file is. Here you can see the .kdm, and it has header, fields, and -1, .kdi file length, .kdd file length, and footer. In the field you can see the field number and index here. Index consists of header, num data dims, num index dims, count per leaf, bytes per dim, num leaves, min packed value, max packed value, point count, doc count, length, data start fp here with is connected to .kdd here, and here index start fp is connected to .kdi here, and here the .kdd has a header, fields, and footer. Field has leaf node data segments. Here the index start fp is connected to .kdi. Here it has header, fields, and footer, and field is a packed index value. Here you can see .kdm complete data structure here now. Here the .kdm consists of header and fields, -1, kdi file length, kdd file length, and footer. Field consists of field number and index consists of header, num data dims, num index dims, count per leaf, bytes per dim, num leaves, min packed value, max packed value, point count, doc count, length, data start fp, and index start fp. Here you can see the .kdd complete data structure. Here you can see the .kdd has a header, fields, and footer. Field has leaf node data segments. Leaf node data consist count, doc IDs, and point values. Point value consists common prefixes and block packed values. Common prefixes consist dimensions, first, second, and in dimension here. Each dimension consists of length and value. Here you can see .kdi complete data structure. Here you can see the .kdi. It has header, fields, and footer. Field is a packed index value, and packed index value consists of right node has not leaf left leaf child and etc. Then left node has not leaf child, left node has leaf child, right node has leaf child, right node has not leaf child, etc. Then right node has leaf child. Here you can see the representation of inverted index. A linear scan is a simple process sequentially going through each line of in the system and checking its parameter, that is condition in a given query. This is precisely how Unix grep command works, and it also works fairly well with the wildcard and regular expressions. If the size of data set being searched size is not too large and then the hardware being used is reasonably powerful, linear search is the simplest way. However, linear search starts showing performance degradations beyond the million median size document. The world around us is too experiencing an information explosion. In fact, the amount of data that needs to be processed to extract relevant information is quadrupled over last 10 years thanks to the advent of connected world, handheld devices and IoT. Linear search cannot be scaled to meet those needs, and so we need something more sophisticated and performant than that can handle massive dataset while still providing relevant result at reasonable speed. Linear searches also limit what kind of queries can be answered. For example, there is no way to define query that seeks close matches of a given pattern. Suppose, for instance, that we search for document with the words flower and sunshine within a proximity of 3 words in a document. Doing so with a linear search is impossible. So also there is no notion of rank result, that is a given query, the result is either a match or not for a linear scan. If we want some sort of ranking, we cannot use the linear scan. An inverted index here is a data structure used to store data in an inverted manner. That is, terms are mapped according to mapped to documents in which the terms appear. Any unique term appearing in any document is made part of the inverted index. As shown in this figure, this data structure proves useful for answering questions like find me the document containing term 1 in an optimized manner. As you can see, a single term search is a constant time operation. To create an index file, fields within a document are first split and tokenized. A sorted list of all the unique terms is created. And the documents that contain the corresponding terms are populated. While being fast for a single term query, inverted indexes can also answer an important class of questions, similarity queries. Here you can see a term and document IDs, here book 1, book 2 and book 3. Here you can see Lucene index structure. The on-disk representation of Lucene index is optimized to be sufficient in reads and writes, and it allows searches into required areas of the index. At the heart of the Lucene lies the Lucene index file format. Post Lucene 4 formats are pluggable using custom codecs and codecs. However, the default file format is what is published on Lucene's official website and what is in the referring to this figure. The basic component to start defining are as follows. Field definitions. Field definitions are stored in an independent file named field infos with the extension fnm. From the with version 4.0 from the official definition, field infos.fnm is going to fnm version, fields count, then field name and field bits, field counts. Here you can see the term dictionary. The term dictionary is represented by two files. The term infos, the TIS file hold the metadata about the term, such as term name, skip information, and document frequency. That is the count of document that hold the term. The TIS file also hold the useful information that helps the Lucene to build its structures for more optimal access of relevant document for a given term. Lucene uses skip data structures internally to make access faster. And this TIS file holds data to help the build this structure. In addition, metadata such as term frequencies in this file allows allows faster access to other files. The term infos index file, the TII, holds metadata to allow random access to the term infos file. The frequencies file extension .frq maps documents to a term. That is, it contains a list of all documents that contains a term present in the terms dictionary, along with the frequency of each term in the document. Positions file .prx positions file extension .prx represent the list of positions at which each term occurs within the document. Here the field definition .ffnm file is connected to a posting list .tis. It is connected to a frequency .frq, and it is connected to a position here, the .prx. As we can consider this as an example here, the interface path, an object that may be used to locate a file in a file system. It will typically represent a file dependent file path. Here you can see the class files. This class consists exclusively of statics methods that operate on files, directories, so other typical types of files here. This interface path is in module java.base and package java.nio.file. As an example 2, we can consider .nfm. The field names are stored in the field info file with suffix .fnm. 3, we are considering class index file names in package org.apache.lucene.index. This class contains useful constant representing file names and extensions used by Lucene, as well as convenience method for querying whether there are file name matches and extension. matches extension, as well as generating file names from a segment name, generation and extension, file name from generation, segment file name. Now we are focusing on basic structure encapsulation. Basic component encapsulation is foundation of Lucene. Now we are focusing on Lucene documents. org.apache.lucene.document provides a simple document class. A document is simply a set of named fields whose values may be strings or instances of reader. Here you can see a term incident matrix. The term document incident matrix is what maps a term to the documents that hold the given term. Simply put, it is a two-dimensional matrix where the column represent the name of the book and the new row represent the terms involved. Here you can see a term incident matrix, books, and here the terms. We can consider org.apache.lucene.document package, the logical representation of a document for indexing and searching. As an example too, we can consider this code segment. Here the class document. Documents are the unit of indexing and search. This is in package org.apache.lucene.document. Here you can see the field. Field is a section of a document. Each field has three parts: name, type, and value. Fields may be text, values may be text, string reader, or p-analyzed token stream, binary, byte array, or numeric number. Fields are optionally stored in the index so that they may be returned with hits on the document. Here we are considering a document and indexable field in package org.apache.lucene.document. The document is a collection of indexable fields. An interface indexable field, which is in the package org.apache.lucene.index, represents a single field for indexing. Index writer consumes the iterable index field as a document. An index field is a logical representation of a user content that needs to be indexed or stored. Indexable fields have a number of popular properties that tell Lucene how to treat the content, like index, tokenized, stored, etc. Note, it is common to refer documents having fields even though technically they have indexable fields. Now we are considering working with docs, working with documents. The class date tools in package org.apache.lucene.document. The date tools is a utility class to make dates and times searchable. First and foremost, the document is something created by a user application. It is your job to create documents based on the content of the files you are working with your application: Word, text, PDF, Excel, or any other format. How this is done is completely up to you. That being said, there are many tools available in other projects that can make the process of making a file and converting it into a Lucene document. The date tool is utility class to make dates and times searchable. Int point, long point, float point, and double point enable indexing of numeric values and also dates for fast range queries using point range query. As an example, we can consider illegal argument exception. If the field name, value, or type is null, or the field's type is indexed, in the constructor public field string name byte array value indexable field type in class field. As an error example, we can consider this error occurred in the environment with Confluence. Indexing fails for content created by LDAP users with null full name. Here you can see a get error, is extracting search fields from attachment, etc. and the value cannot be nulled. Java.lang.null point exception value cannot be nulled, and at org.apache.lucene.document field, etc. Now we are focusing on Lucene util tools. Org.apache.lucene.util contains a few handy data structures and util classes, that is fixed bit set and priority queue. Here we can consider package org.apache.lucene.util. This is some utility classes. As an example 2, we can consider this class query builder. Create queries from the analyzer chain. Here, for create boolean query. Create a boolean query from the query text. This is the field, and this is the query text. Here the create a price query from query text. This is the field and this is the price query. Here create a minimum should match query from the query text. This is the field name, and this is text to be passed to the analyzer, and this is the of the query terms 0 to 1 inclusive that should match. And this query build is in the package org.apache.lucene.util. As an example 3, we can consider class bit, this code segment, and class fixed bit set. A bit set of fixed length number of bits backed by the accessible get bits long accessed with an index, implementing bits and doc id set. If you need to manage more than 2.1 bits, use long bit set. This is in the package org.apache.lucene.util. As an example 4, we can consider class priority queue T. A priority queue maintains a partial ordering of its elements such that least element can always be found in the constant time. Puts and pops require log size time, but the remove cost implemented here is linear. This in package org.apache.lucene.util. As an exception example, we can consider class thread interrupted exception thrown by Lucene on detecting that thread.interrupt had been called. Unlike Java's interrupted exception, this exception is not checked. This is in package org.apache.lucene.util. As an error example, we can consider this occurred in the environment Lucene 6 and build.py package. Here you can see command java c -x max errors 10,000 etc. And here you can see failed, an error package org.apache.lucene.util does not exist. Import org.apache.lucene.util string helper etc. This is end of my presentation. Thank you very much for watching it.